Okay, it looks like we're almost ready to go. Hi everybody, welcome to everybody to the hands-on egocentric research with Project Aria tutorial. My name is Andy Miller. I'm a research product manager in the research reality team working on Project Aria. We've got a really jam-packed schedule. We're going to talk a little bit about what Project Aria is, the motivation behind it. Then we'll move on to learning about the Aria research kit. This is a research kit we provide to academic researchers for independent research. After that, we'll follow on introducing new tutorials, some new data sets and challenges that are going to be open source so that we can accelerate AI and ML research. And finally, we'll close with a Q&A. So we've got a lot to get through. Without further ado, I'd like to introduce Ruben. You can talk us through the always on the team chat.
Thanks for joining us here, and of course, if you're online watching this later too. I'm going to give us some motivation for Project Aria. Hopefully, most of you in the room for the tutorial, because you do know something about Project Aria. It's our second CVPR tutorial and workshop combo. And it's always good to sort of get back to the roots of what it is about, what we're trying to achieve, and why we need you and the community working on this with us. Okay, so it's the wrong direction. Good start. Okay, so here's a quote. I'm eager to find out who knows about this quote is. Let me speak to you. If you were supplied with a computer that worked all day long and was instantly responsive to every action that you had, how much value would you derive from that? Now, my assumption is very few people know where this quote is from. Let's check. Anybody? If you put your hand up from the national labs. Okay, so these communities is what I really want to speak to you about. Basically, are separate. This is a quote from the very famous Engelbart, who basically introduced the modern computing paradigm in around 1968 with a demo, the motherable demos. I may have heard of that. And the motherable demos is basically the very first time that things like the graphical user interface, together with a mouse-powered, basically Windows like PC experience with a spreadsheet and network PCs, was actually shown in the world. Pieces have been developed in different labs, but no one put them all together into a complete experience of a future computing lab built for humans who can do that with non-paper, but completely digitally. Now, from there, essentially, the explosion from what was the original Alto that they were using and building on top of that demo from 68 until about 73 led to the PCs, ultimately to Mac, when Steve Jobs once visited Alto and saw basically the research, saw that was the future for basically how things were going to interact with computers. And then essentially over our generation, sort of like, from the 90s and the last sort of like decade and a bit, into the early 2000s, the mobile phone came on. Now, there's not a single person in this room who didn't have a mobile phone in their pocket, and that is the true sort of like child of all of that. It is a graphical user interface in 2D, driven by essentially a pointer with a finger instead of a mouse. It's connected to the internet. It enables billions and trillions of dollars to flow. The most powerful and influential companies on the planet are basically in the business of building those devices and giving them to billions of people. Okay, so what's that got to do with Aria? Well, let's get into it. We're now here with virtual mixed reality devices. If you didn't see it, Apple is saying that they're releasing the Apple Vision Pro, which is a mixed reality device. And of course, Meta has been developing products in that space now for good 8 years, including multiple releases of essentially untethered headsets, and a lot of progress is being made in this space of VR and mixed reality. These are wearable computers, and they push beyond the capabilities of those 2D rectangles that you keep in terms of the user interface by embodying you within the experience, so that your body becomes part of the control, and also your perception system can start to be liberated from the 2D windowing systems to a full 3D experience. Now, the way that we like to think about this is that it really is providing a new class of wearable rendering surface. And they take the form of these three visual, auditory, and haptic modalities that otherwise are completely essentially limited in a 2D windowing system. And of course, to enable a visual rendering system that's safe to 3D means a lot of technologies computer vision communities have been building for the last 30 odd years. Auditory experiences, including spatialized audio, can be possible with these wearable devices, not possible with laptops and mobile phones. And actually, there's a future of haptic interaction where effectively you can interact with virtual objects and real objects alike and blend or mix reality together. Okay. But something's missing from this experience. So whilst it clearly is an advancement beyond the mobile phones that we have, it's not everything. Let's return to the equation, the end part. So a computer that works all day long and is instantly responsive to every action. Let's think about this. Now remember, he was saying that quote whilst demonstrating the precursor of computers and mobile phones. What would it mean to have a computer that actually works all day long? Well, I'll put it to you, number one, it would have to go everywhere you go.
Because if you have to be tied to a desk or to something where you can't carry it with you everywhere into the coffee shop, even, out in the public spaces, in your cars, on a plane, etc. If you can't do all those things, it obviously can't work all day long with you unless you limit your experience of reality, for example, to a desktop PC. And what does it mean to be instantly responsive to every action that you had? I put it to you again that whilst there are some things that are essentially immediate mode interactions where you want a computer to give you an answer based on a very short amount of input, actually, most of the things that you care about throughout your entire day, week, month, year, decades of living actually are contextualized not by a single moment's information, but by exactly minutes, hours, weeks, years, decades of understanding you. And of course, that's why you have friends and relatives that you love and want to spend time with, and your colleagues eventually get to know you and they work more effectively with you and vice versa because of that long context window. So whereas PCs and mobile phones work instantly and responsively to a very simple interaction, a simple context, where your finger is on the screen or where your mouse cursor is or what your keyboard immediately says, it cannot possibly be instantly responsive to an action that requires context that may be months in the making. What does it mean to have a computer help you with your health condition if all it can get is basically a very simple, hey, Siri, I want you to help me with my health condition, and it has nothing else about you? That's not going to be possible. Okay, so I'm going to claim that essentially whilst mixed reality for wearable immersive experiences is very much here, and we see that from two big companies making products, essentially that's not the be all and end all of computing. Okay, what else? Well, now AI is here. So whereas in CVPR last year, if you were here, and many people may have heard of GPT, not everyone will have experienced it. Now, I doubt there's a single person in this room who hasn't had a chat GPT experience. In fact, who has used chat GPT? Amazing. That is 100% of the audience. Okay, so that's 1 year's worth of development in AI. But interesting, AI is here, but there's a gap there as well, right? Who can think what that gap is? Well, if you've had that experience with ChatGPT, you will know that it can answer those kind of immediate questions or things where there's world knowledge that's come from the internet, but it can't know about you unless you literally type it in. Hey, I'm Richard, I'm a 40-year-old, I like cycling a lot, I just crashed my bike and I'd like to, and you keep going and you just have to put it all in there by typing it. It's missing context. And it's that we call contextualized AI that we think actually is the thing that really needs to happen, that can only happen if you have two things, and that is context of you, and that comes from these components, basically all-day wearable devices, and also the ability to essentially have machine perception, take the data from those devices and turn them into signals that then things like AI can actually work with. AI cannot consume an entire day's worth of egocentric imagery. It's just too big. We'll see how big some of that is in the various different talks later on today. But when you do put those two together, you get contextualized AI, and it's a very new class of problem to solve for. You have to solve the problems with wearable devices, machine perception, and you have to put it together with AI. These fields are not separate. They're going to be combined. Okay. So this is the always on AI challenge, and the kind of essentially nugget or view of the problem that we're trying to solve with Aria that I want to give is to first of all plant you back in reality. In reality, you wake up, and if you're a glasses wearer, like me, you sort of like fumble for your glasses to put them on because otherwise you're not really going very far. And from that point on, your day kind of unravels in good or different ways for everyone, in subtly varied ways. And the question is, what would a machine perception system through an entire day have to capture to be useful for you? That is a question, and you can answer it. And realistically, what we're trying to do with Project Aria is to find the machine perception algorithms that get that context throughout your entire day, multiplied by through weeks, months, ultimately years, and bring it to bear with AI to enable contextualized AI. So always on AI, context and machine perception, always on. That's the other differentiator. There's lots of AI. There's lots of what you can think of as very short-term contextualized AI, a video clip, multimodal that lasts perhaps 20 seconds. That's not the same as machine perception and AI working together that is never off. It has to be on, otherwise it's going to miss those subtle details that matter to you. So what I claim is essentially that if we're going to enable useful, lifelong, always on AI, you're going to have to solve these problems. You're going to have to solve that context gap, get the context of a human, get it into the AI's memory. You're going to have to solve the wearable machine perception problem to get that context, because otherwise you're not going to be able to get the data from the user's life. And you're going to have to solve these new low power, small form factor constrained machine perception challenges to enable that wearable device to become real, because we can't walk around in those big mixed reality headsets. It's basically painful after a few hours. The battery runs out. And that leads to this new class of machine perception, which I think we're just all starting to be aware of. And perhaps, this is one of the first times that you may have heard about it. It's distributed machine perception. So when we look at the really hard problems of solving for those constrained form factors, ultra low power, always on, what we find is challenges that we don't think you can solve in a single device, but you may be able to solve if you have a federation of devices working together to solve those machine perception problems. So I'm just going to leave those with you as basically the new grand challenges in computer vision. And this first one, this wearable machine perception, is exactly where Aria kicks off. So going from something like a Quest Pro into a glasses form factor is non-trivial. We're going to hear about the various different challenges today. Okay, these are the three problems I want to leave you with before I hand back to the team to take you through some of the amazing and opportunities that are presented with Aria devices and services. These are what I think researchers should be working on basically for the next decade to solve this context gap and enable contextualized AI. First of all, we've got to get to grip with the fact that the data coming from these always-on devices are so massive that the current paradigm of machine learning, which is about end-to-end learning, cannot work. You cannot capture a person's year with egocentric data from a device like Aria and hope to train a transformer end-to-end. That data set is somewhere on the order of 1 to 10 petabytes just for one sample. So you're going to have to solve the compression problem. Now, that might be tokenization. That might be things like perceiver IO that try and compress into a latent space. It might be very special, very tuned algorithms for machine perception like SLAM and object detection, etc. But that is the challenge, compressing reality and basically going from petabytes of egocentric data down into something that actually can be consumed by current and future generations of machine learning. Even if you can do it in principle, so take these data sets, run them on giant GPUs, show you can compress reality, you then need to do that on these form factors that basically are on the order of milliwatts of power. To give you an idea of the sort of power we're talking about, this is a Project Aria device. There's an LED in the corner. It's a bit smaller than this blue one here. That LED takes around 5 milliwatts of power. We believe that the entire device will have available to you 100 milliwatts of power for the entire day. And the LED is already taking 5 milliwatts. A normal mobile phone camera takes over 100 milliwatts simply to take a 60 frame per second video. And imagine the kind of data that comes off a Project Aria device today. it takes a lot more than 100 milliwatts. So you're going to have to solve all those algorithms on tiny amounts of power. And that necessitates an entirely new class of thinking about algorithms through a very different view of sparseness of information that today we're not used to. We're used to putting the data sets through big machine learning algorithms, then maybe cranking the handle of quantization and sparsification after the fact. But you're not going to be able to do that when you've got to be constrained with tens of milliwatts of power. You need new classes of algorithms. And this is when we get back to, well, maybe one single device doesn't need to solve everything all the time. And that's distributed machine perception. Very excited to talk about that with everybody here. And there was a great workshop at ICCB exactly on this topic just 2 weeks ago. Okay, so I'll leave you with this thought. If you are in an area doing your PhD or a postdoc or in general researching, I really think this is the area where the next breakthroughs are going to come, basically in combining machine perception on ultra low power, always on form factors like glasses. Because if we can solve that, then we can unlock contextualized AI. And it's contextualized AI that really will enable what we call the second great wave of human-oriented computing that will elevate us past these kind of 2D rectangles that have no context into devices that are useful for you everywhere you go, all the time, for everyone doing pretty much everything they want to do. With that, I'm going to hand back to Prince. Thank you, everyone.
Hi, all. I'm Prince Gupta. I'm a research product manager in the Reality Labs research division. And today I'm going to tell you about why Project Aria is the best device in the world for egocentric research and how you can leverage it for your own work. I'm going to do that by first introducing Project Aria and then telling you about Aria Partner Program, which is available to universities, startups, and corporations to access Project Aria. Richard talked about always-on contextualized AI. If you want to build always-on contextualized AI and you look at the landscape of devices which are available to you to do that, you can map it in these two axes. First is device capabilities. So you can have devices like the Quest line or even HoloLens or the new Vision Pro device. They have good sensors on them. So they have quite a good sensors. But if you look at the other axis, which is form factor, they don't have a great form factor. They weigh somewhere close to in the order of 500 grams. So you can only wear it for about 30 minutes or so. The other set of devices are like GoPro devices or Vuzix glasses types of devices, which have good form factor for longer duration of use, but they don't have the right sensors which are needed for egocentric research. And therefore, we discovered that there is a gap in the market of a device which has the right form factor, which you can wear for all day of use, and also has the right sensors. And that's why we introduced Project Aria. Project Aria is a device which lets you capture all these rich multimodal sensor data information in a wearable form factor. Project Aria is not a consumer product, and it is not a prototype. It is what we call is a research tool. Project Aria is packed with sensors. It has the 2 SLAM tracking cameras on the side, a high-resolution RGB camera in the front as well, 2 eye tracking cameras, so in total 5 cameras, 7 microphones all around the glasses to be able to capture spatialized audio, 2 IMUs, magnetometer, barometer, GPS, Wi-Fi, Bluetooth, 128 GB of onboard storage, all this packed into a 70-gram device. And there is an onboard battery as well, which can last up to 1 to 2 hours of use on a continuous basis. And you can always connect a battery pack as well for all day of use. In fact, let me show you what all the sensors actually look like. Okay. So on the top left, you can see the 2 SLAM tracking cameras, which are running live. The RGB high resolution camera as well. These are my eyes over here. So these are the 2 inward facing eye tracking cameras. All the other, these graphs are for the various motion sensors on the device, the IMUs, magnetometer, barometer. This last one over here is the 7 microphones around the device. So this is the full set of sensor suite, which is available on these devices. But just having great sensors is actually not enough. You also need all those sensors to be perfectly aligned and timestamped. Therefore, on Project Aria glasses, with the SoC on the system, we make sure that they are all running through a common clock, such that all the sensors are timestamped with the common clock, and you get access to the raw sensor data as well as the timestamp for each of those sensors. What this allows us to do is that if these were not aligned, then they would be drift in the system over time. What this allows us to do is that in the whole system, there is no drift at all as long as you can run the device. So this allows us to synchronize all the sensors on one Aria device. But what if you need multiple Aria devices to be synchronized as well? There are many applications in which you need time alignment across multiple users. So in this video, you can see 9 different users who are wearing Aria glasses. All the video feed and all the other sensors which are coming from these 9 different devices are synchronized together. I mean, think of building applications where you have 2 users collaborating on a whiteboard and you want to align sensor data of those 2 users. You can do that through these systems because you can connect the 2 Aria devices in that case just on a single Wi-Fi hotspot and be able to synchronize the sensor data coming from multiple Aria devices. So Aria devices have great sensors. You can synchronize all the sensors, and you can synchronize multiple Aria devices as well. Another thing which is quite unique about Aria devices is that it has very robust calibration. So all the sensors on the device, their position and orientation are highly accurately calibrated at the factory. But these devices are somewhat flexible, even by the act of like wearing the glasses and then taking them off, the glasses go through a little bit of twist and turn. And the calibration of each of the sensors vary a little bit, which is not perceivable by human eye, but the algorithms detect those variations. Therefore, we have another feature in the system called online calibration, which adjusts for those slight movements as the system is running. So we support both robust calibration at the factory and also online calibration for the various algorithms. But so, now you have a good understanding that Aria is a very powerful device. As Spider-Man said, with great power comes great responsibility. So to make sure we are innovating responsibly, we support a number of privacy features. At a hardware level, the glasses have 2 LEDs, one outward-facing LED, which is visible up to 25 feet. So if there is any recording going on with the glasses, the bystanders will be able to know. There's also an inward-facing LED, such that the wearer is always in control as well. The wearer always knows when the glasses are recording. There is a physical privacy switch on the glasses as well, which serves 2 functions. If the glasses are recording, and in between you turn on that privacy switch, it is going to delete the current recording which is going on. So it will completely remove it. And second, if the privacy switch is flicked on, then you cannot turn on the recording on the glasses at all. So it'll make sure that no sensors are able to be turned on. These are some of the hardware features on the glasses. On the software side, we support 2 different anonymization models for datasets which are collected in public spaces. We anonymize faces and license plates so that we make sure that we remove personally identifiable information from these recordings coming from the glasses. Okay, so I hope this gives you a good view of what these classes are, what they are capable of. Now let me tell you about the Aria Partner Program. When we started Project Aria, our goal is to accelerate machine perception and AI research, which is needed for future AR classes. We do that by serving 2 different communities. Of course, we use these classes quite a bit internally at Meta for various types of research. But it is equally important for us to partner with the external research community, which is all of you, academics, startups, and other corporations. The reason is, at Meta, we firmly believe that we're building an open ecosystem and we're building an open metaverse. Therefore, it is strategically important for us to partner and thrive and foster this open science in the community. And to that end, I'm very happy to announce that we're, announcing and launching a new website, projectaria.com, for all our partners, where you can go and get access to all the information about Project Aria in a single place and access various resources like data sets and other GitHub repositories, everything in a single place. Now, we partner with different partners by offering two different things, which is part of the Aria partner program. The first is the Aria Research Kit. For Aria Research Kit, you have to apply through our website. The Aria Research Kit consists of the classes, a number of machine perception services, and client SDK. And also we have Open Science Initiative. For Open Science Initiative, we have open source data sets, tools, and models, which are available on GitHub and also on our website. So you don't have to apply for it at all. You can just access it in open source. So these are the two ways in which you can access Aria. And we have dedicated sections on each of these two areas throughout the tutorial today. But at a high level, this is our engagement model with other partners. One, the data that you collect using Project Aria is your data. The IP that you develop using data from Aria is your IP. What we are interested in here is to learn together. We want to be able to discover new use cases for future AR glasses and also do new research in the field of egocentric perception. All we ask is that we all agree to a common community guidelines. These glasses are very powerful, and therefore we want to make sure that these are used responsibly when we are using it out in the community. Therefore, we have a set of common community guidelines to make sure that we are all agreeing to using these glasses responsibly. So with that, let me show you two different examples of how partners have used these glasses so far. So let's see if those videos play. Ed, if you can turn the audio on.
I have retinitis pigmentosa, which is a genetic disorder. I've been losing my sight since birth. If I'm in a completely new place, there's no way to know where I'm going on my own. There have been times when I would just be put somewhere, like maybe, in a room or just at a gate, might have to wait over an hour for someone to assist you to get to where you need to go. Pretty degrading, huh? You just feel like you're not part of the society that can just stand up and go and do what they want to do. NAVCOG can change that. 2 stars on your right.
What we're working on is a turn-by-turn assistive technology that we've developed at Carnegie Mellon University starting in about 2014. And it helps to give people with visual impairment the ability to navigate in unfamiliar environments by presenting audio instructions at precisely the right moment, helping them to get from A to B.
There is a ramp, 140 feet. For years, I've gotten around with the assistance of my guide dog, Flirt. I love and depend on her dearly, but a guide dog is not a navigation system.
So one of the biggest...
So I think that example is a very powerful example. It shows you, how Aria devices can be used to provide accessibility features for visually impaired people to navigate in spaces. Now, let me show you. So that was a collaboration with the Carnegie Mellon University. The next example I'm going to show you is with a corporation, BMW. So let me play the video first.
You might assume that it is simple to deliver virtual experiences to passengers.
But it's not so easy.
Moving vehicles pose a challenge because the sensors get conflicting signals from the device's motion within the car and the car's motion within the world. We collaborated with BMW to incorporate information from a BMW car's sensor array into the tracking system of our Project Aria research glasses. It enabled Meta to create an in-vehicle tracking system that simultaneously calculates the device's location relative to the car and the moving car's location relative to the world.
We are excited about this progress because this could mean that travel is going to be more enjoyable, more social and productive, more relaxing, or more fun.
Is this a big deal? That's a pretty big deal, yeah.
So these are just two examples, but I'm really looking forward to what all new use cases that you all as a research community can create using Project Aria. So then to go over Aria Research Kit, let me introduce you to Sach Lakhwani. Thank you.
Thank you, Prince. So as Prince mentioned, there's two ways in which partners can engage with Project Aria. One is through the Aria Research Kit, and the other, oops, no. There we go. One is through the Aria Research Kit, and the other is via Open Science Initiatives. This section is going to focus on the Aria Research Kit. Now, the Aria Research Kit is the program through which we provide our approved academic partners and commercial partners with glasses of their own for their research. Now, there's three pillars to the Aria Research Kit program. One is the glasses and the companion app. Second is our machine perception capabilities, which we provide as a service to our partners. And the third is the client SDK, which enables real-time streaming of data from the Aria glasses. So first we'll get into the glasses. As Prince mentioned, the motivation behind building the Aria glasses was really to provide researchers with two things. One is the ability to collect multimodal egocentric sensor data in the types that we expect on future AR glasses. And the second is to do this in a socially acceptable form factor that enables long duration usage that is ecologically valid. So it does not impact the activities and behaviors of the wearer. The second is the mobile app. Now, we've designed this mobile app as a convenient way of controlling the device when a researcher is in the field collecting data. So this provides basic features such as starting and stopping recording, as well as configuring the sensor data to collect. And then finally, we built a desktop app for later in the researcher workflow when the researcher is back at their office. And this provides features such as managing the data that's on the Aria glasses, as well as accessing our machine perception services. Okay, this isn't working. The second pillar of the Aria Research Kit is the machine perception capabilities that we offer as a service. Now, the way this works is that after recording Aria data, a researcher has the option to select one or more machine perception services via the desktop app. They then upload their data, we process it, and we return the machine perception output. One very important point that I'd like to stress is that immediately after processing this data and returning the machine perception output, we delete the data from our servers. So as Prince mentioned, the data that's collected by our partners belongs to our partners and our partners alone. These machine perception capabilities are enabled by a set of proprietary algorithms that are designed specifically for the Aria device. So what this means is that they provide a better robustness and accuracy relative to off-the-shelf open source algorithms. So really, like our goal in providing these machine perception models is so that our researchers have a rock solid foundation upon which to do their research. We offer a number of machine perception capabilities, including 6DoF trajectories, online calibration, eye gaze vectors, and semi-dense point clouds. Additionally, we're working on more machine perception capabilities to offer via our service, including multi-sequence trajectory, eye gaze reprojection, and a few more that we'll be announcing in the future. This video gives you a kind of quick preview of the types of machine perception capabilities that we offer, and Jacob's going to be going into a lot more detail on this in the future. The third pillar of the Aria Research Kit is the client SDK. And this is important in that it enables real-time research and the development of real-time experiences. So the client SDK, broadly speaking, offers two capabilities. One is the ability to programmatically control the glasses. So start and stop, sensor configuration, all of the capabilities that exist within the mobile app. And the second is that it enables real-time data streaming to an offload compute device for real-time data processing. So these devices can include things like glasses, computers, compute puck, etc. Additionally, we also provide sample apps, and these sample apps are meant to make it easy and intuitive for our partners to build apps on top of the client SDK. So I'll give you one quick example. Sorry, the clicker's not working very well. There we go. I'll give you one teaser example of an app that's built on client SDK. So what you're seeing here on the left is a researcher who's streaming data wirelessly in real time from the Aria glasses to their desktop. And on the desktop, you see object detection and tracking models being run. Carl will go into a lot more detail on the client SDK later in this presentation. So now you have a sense of the capabilities that the Aria Research Kit offers and why they're important for your research. But ultimately, our goal of coming here today is so that you as researchers begin to crystallize in your minds how you may be able to use Aria for your own specific research interests. And to motivate that thinking, I'll provide a few examples of research that we've done internally leveraging Aria. Now, I love this first example, magnetometer mapping. And what this does is highlight the rich sensor suite and machine perception capabilities of Aria. Traditionally in mapping, what we've seen is maps that have been derived from visual sensors. Here we're looking at new map modalities. We take the precise location that's derived from machine perception services and combine it with the dense measurements from the magnetometer on the Aria glasses to create a 3D field map of the environment. The second example here is the human positioning system. Now this example highlights how Aria can be used in the context of system research. So here we use two Aria and a motion capture suit to capture the human body pose in the wild. So here what you see in the video is an observer and a performer, both of whom are wearing Aria glasses, and the performer is also wearing a mocap suit. On the left, what you're seeing is the trajectory of the observer and the performer, and on the right, what you're seeing is the body pose of the performer reprojected in the RGB frame of the observer. And the third example is an egocentric CV task that is also enabled with the 6-DoF trajectories provided by our machine perception capabilities. Here we use Cube RCNN to detect per frame 3D bounding boxes of objects. So now you understand the capabilities of the Aria Research Kit and a few examples of how Aria can be used for research. The next natural question is, what is the process to get glasses of your own for your research? So a common question is, what is the criteria when it comes to approving partners for the Aria Research Kit? We have two high-level criteria. One is that we're looking for researchers who have a track record in egocentric machine perception and AI research. And the second is we're looking to partner with researchers who have an interest in exploring new AR, VR use cases for commercial and consumer applications. Given what you've heard today, if you're interested, go to projectaria.com, and there's an application form where you can apply for the Aria Research Kit there. There's one final message that I'd like to leave you with. This year, we're committed to significantly scaling the impact that the Aria Research Kit will have on the research community. And we're going to achieve this in two ways. One is that we're investing a lot in improving Aria as a research product. You're seeing a lot of these new and exciting features today, but this is just the tip of the iceberg. We have a roadmap full of exciting new features that will be shipping over the course of this year and beyond. Secondly, we're scaling our capacity to bring on new and more research partners. And one example of this is the Ego 4D Consortium, who are extending their work on egocentric video understanding, leveraging Project Aria data. So this is going to be a big and exciting year, and we're excited to be on this journey with many of you in this room. And with that, I'll hand it off to Jacob, who's going to get into a lot more detail on our machine perception services.
let me see that I don't get the buttons wrong. And how much more detail I can actually go into in what, 10 minutes. All right, let's go. That's backwards. It is very confusing. Cool, machine perception services. So as introduced, the idea behind machine perception services is to provide a common basis of machine perception capabilities that anybody who uses either Aria devices as a research partner or any data sets that are created from Aria data can build on top of, rather than having to like re-implement them or redo them over and over again, right? Richard in the very beginning introduced the ambitious mission that we are on with Project Aria to foster egocentric machine perception on the path to contextualized, personalized AI for that to become a reality. And these are kind of, you can think of them as fundamental building blocks that we think are quite important to build on top of, and that we want to provide. Back again, forwards. All right. And we do that by leveraging machine perception algorithms that we have internally in Meta. A lot of them are very similar to what you'd find on like AR and VR headsets, for example. And thus it's kind of fair to assume that they will exist in the future on egocentric devices as well. All right. So as I mentioned, you can get access to them either if you're an approved partner and you have your own device, you can collect recordings, upload them to Meta servers, get the processing done and get the results back downloaded. We are not keeping any of the data. It's really just ephemerally there to process the data sets. And then second, we're also including the same output in any data sets that are made up of Project Aria data. All right, so what are those capabilities? And you've seen many of these videos before. The first one, super important, just 6 DOF poses, right? Localization of the device in space. And that is really what powers 3D machine perception. So the first thing we offer here is just for a single recording, basically localize that in a consistent coordinate frame. We are using a proprietary visual inertial SLAM system with the VIO front end, plus a backend optimizer that gets sort of the maximal accuracy out of it. There is both a open loop trajectory and a closed loop trajectory that provides poses in a single drawing coordinate frame for the entire sequence. And it is built in a way that is really meant to work anywhere and always, right? As Richard introduced, it's really important for that personal context that this doesn't just like these devices and these algorithms don't just work in lab settings, but actually work whatever you do during your normal life, right? Like doing motions that you would do normally without paying attention for algorithms to not break. So it's really built to work wherever you wear devices, indoors, outdoors, biking, and so on. It's very accurate. The accuracy is about 0.2 to 0.4% of like translational motion, which translates to about 1.5 centimeters in a room about this size, I'd say, in terms of global accuracy. And then we also include things like some uncertainty estimates and information about when it works and when it sometimes doesn't work. Last but not least, because it's all made for multimodal sensor fusion, all the poses are not just for individual frames, but at 1 kilohertz. So you get poses for every single sensor on the device, no matter whether that's audio or video, for example. Second, obviously, it's important to get poses also for multiple recordings, either from the same device or from different devices in the same space. This is something that we are working on, and I think it's on the roadmap for Q3. So if you're a partner, you can upload many recordings together and get them all localized in a single coordinate frame. And here I'm just showing a video from the Aria pilot data set that did that for, I think, a couple of dozen recordings that were all captured in the same flat. Prince already teased this a bit. We're also doing online calibration. One of the requirements for doing this is very, very accurate geometric calibration of all the sensors involved. And as much as we try to make Project Aria glasses as rigid as possible, it's only so possible in the form factor it has. So there are some deformations if you use it, especially if you, for example, put it on and take it off. So we give, in addition to the poses, also a per frame online calibration. that gives you all the sensor calibrations at frame rate, essentially. And just here on the slide, you can see a concrete example from an actual sequence, from actual recording, where the user kind of holds the device in their hands and then puts it on the head. And you can see that actually the left and the right cameras bend by about 0.5 degree between them just from that motion. All right, I'm not going to go further about the exact output format. We have a beautiful new website that has all the information, and you can find all of that there. All right, second up, seen a lot of point clouds in the presentation so far. That's what this one is about. It simulates point clouds computed effectively from the SLAM cameras as passive stereo tracks, and they provide a really good understanding of the environment that the device is being used in. They obviously only cover static things, so they don't triangulate anything that's moving. They also provide 2D tracks. We output not only the 3D points, but also where they are visible in which image, when. So you can use those as like a sparse optical flow or to get visibility in 3D space. And the whole thing also works outdoors. Here's an example of somebody walking around in Seattle. And this is the reconstruction you get literally from somebody walking down the sidewalk with a Project Aria device recording. Again, all the details on how it looks like is all on the website. And here's an example that I think Satch already showed, how that looks like on the Project Aria pilot dataset, bundling together, I think 20 or 30 different recordings of everyday activities, all localized and all with point clouds in one frame of reference. All right. So much for the outwards facing sensors. Now, very important, is also about what the user is doing in the scene. And the first one here, or one of the probably most important signals about what the wearer actually cares about, is eye tracking. So we provide eye tracking as a machine perception service as well. It provides the eye gaze just as a single ray anchored like in between your eyes, pointing out in the scene. With an error of about 2%, 2 degrees, which goes down to about 1 degree if you do a personalized eye tracking calibration, which makes it a bit more accurate. And you can see here in the video how much information it actually gives you about what the person is actually up to. Usually the eye gaze precedes even what they're doing, so you know what they're about to do. Again, all the information is on said that the third time now, all the information about that is on the website, so you can find it there. Cool. And last but not least, I want to just give a quick teaser about hand tracking. This one is work in progress, so we don't have it quite yet, but we're working on it because obviously hands are yet another really important signal about what the user is doing in the scene and can help with a lot of things. And we really want to make it easy for people to build on top of a solid, stable hand tracking algorithm for whatever they want to do with Project Aria afterwards. And with that, I'm going to hand over to Carl to talk about the software ecosystem.
Thanks, Jacob. Let's see whether I get the clicker right. Oh, no. All right. Hello, everyone. My name is Carl. I lead the software engineering team that builds all the softwares and services for Project Aria. So here I'm going to give a very high-level overview of how the software ecosystem look like. What Prince and Sash has presented is more of a product surface view. There are verticals that's applied to different customers, as you will. But of course, we don't build software separately for different customers. We build a kind of a horizontal software ecosystem that supports all the use cases. And we want to build it as streamlined, as user-friendly as possible. And here is what I'm going to talk about in this software ecosystem section. So the overall software ecosystem covers 3 major use cases. One is device control and real-time system integration when you have Aria running in streaming mode. And last but not least, data processing when you recorded the data and then you want to run the machine perception services or just natively use the raw data to conduct certain research. So the first 2 use cases are bundled together into what we call the client SDK. And Sash touched on that. It's a set of APIs that we expose those functionalities, and we provide a set of sample apps such that you can just use those as reference to start your building of the application. So just as all software, development is built as layered development, right? So this is just on a very high level. On the Aria glass itself, we run a bunch of system services, including recording services, DDS messaging, and TickSync. And before, in 2022, when we launched the Aria tools, we didn't expose this layer of software SDK. So even for partners who get Aria glasses, they won't be able to, programmably control the device, and they wouldn't be able to build real-time demo on top. Of course, we get a lot of feedback from the partners who get the data, the device, and they really want this. Therefore, we build this layer of software APIs to give you access to all of that. And on top of that, we can build, well, our first-party applications are built on top of that, obviously, right? But it enables third-party applications to be built for research, prototype, and demos and use cases. These are just a few examples that Sash already showed. Mobile apps, desktop app, they're already building on top of our client SDK, and we're releasing a device control CLI tool, so you can use command line and scripting to control the device itself as well. And this is just another example of the real-time system. This is just some code snippet for you to start Aria streaming. I think folks have seen the previous video that Sash has shown. This is another demo. The difference is, see, right now we're not streaming through Wi-Fi anymore. We are connecting Aria glasses to a little NVIDIA Orion puck, and we run all of those machine perception capability that Jacob just showed in real time in this mode. So we have real-time SLAM tracking, our internal hand tracking. We have object detection based on gaze, which wherever you look at, we prompt that segmentation, right? And on the right-hand side, we have the semi-dense map, the trajectory, the hand tracking, everything in one single frame of reference. At the same time, we're also doing real-time audio transcription. This is one of the internal contextualized AI demo that we're iterating on. But of course, when we give this to the community, I'm pretty sure there are many people who will come up with even more impressive demos and applications. Oh, this just played again. But the next part is a set of, the client SDK and the client SDK, which includes the device control and real-time system. They're kind of a packaged library with APIs that you can call. They're not really open sourced, right? But you can build application on top. The other set of tools that we're releasing are truly open source tools. You get the source code, you can directly use it. This is around the data loaders, visualization, calibration tools for Aria. It's very easy to use from a researcher point of view, which Vijay will give you a very quick demonstration in this room, how easy it is for everyone just to load the data, get running with your research. The next one, the machine perception services that Jacob talked about at the moment is accessed through the desktop app. You do a bunch of click and then everything is uploaded. We are very soon will release a machine perception CLI tool where you can do scripting and batch processing. It's easier to use if you have a large batch of data that you're collected through the Aria glasses. So this is just a demonstration of how currently you use the machine perception service. It's a bunch of clicks. You select the sequence, you select the capabilities that you want, then it's uploaded, right? Later on, it will be downloaded. All right, looking back on the history of how the software ecosystem has evolved. In 2022, we launched the Aria pilot dataset together with a bunch of data loaders and visualization tools. Everything is provided through a Docker image, so people can use it basically as a prepackaged thing. We got a lot of feedback from our partners as well as the community that they want more, right? They want it to be more streamlined and more easy to use, and they want to also be able to customize more, and that is what we have done for the last year. So we provide now a new data loader that is compatible with all the data set that we provide, as well as the MPS service. It's all the same format. It's one single loader. We have even more visualization tools. So whatever we provide through the machine perception services, you can visualize it, see what is going on, check what is wrong, debug, right? We provide a pretty comprehensive data device calibration loader. You see our PM and Jacob both talk about the calibration, how we're proud of that, right? So we provide that tool to load all the calibration on every single frame through every single sensor stream. The installation to get people up and running is really simple. Right now it's pip install, single line, and you will be up and running very quickly. We provide Jupyter Notebook quick start samples. This is one of the bigger feedback. Our team starts as hardcore C++ coder mostly, so we provide it to that way initially. Then we learned it from the hard way that people really like Jupyter Notebook and Python, and they wanted it, so we built it, right? We still have the CMake native C++ built in case you want to build even fancier visualizers. We'll provide a machine perception CLI tools, as I just mentioned, and an all-in-one wiki for both partners who has the device and or partners who use mostly the data sets to look for all the information that is needed. All right, I think this might be the last slides. I want to give you a high-level software release roadmap so you understand what is coming and when. Right. In 2022, we released a set of pre-built desktop tools, mobile apps, and the set of data tools, very basic ones, right, to load the data, visualize them. And we released head poses and eye tracking. In this CVPR, at the moment, if you go to the website, you will see our current release. That is the set of Aria tools that on the previous slides that is already available. You can use it today. We have the Aria wiki that is available right now if you go on the website. We're also releasing the point cloud that Jacob's talked about, the in-session eye tracking calibration. This might be a new piece of information that I need a little bit of technical explanation. So when you wear the glass, you have eye tracking camera looking at your eye, and then you have a eye gaze vector from the center of your the glasses, which is reflecting your eye tracking, right? That is dependent on the position of your glasses. If you move the glasses, that will change, will become inaccurate. So we developed a tool from the companion app that when you wear the glass, you look at the tool for a few seconds, it's calibrated within your session. So your eye tracking becomes super accurate. In Q3 is the exciting moment where we will release the client SDK, streaming API, synchronization, device control CLI. We'll also release the multi-device, multi-sequence alignment through the MPS services. Towards Q4 into ICCV, I think we're going to have a major release there, which includes a fully revamped desktop app, which is even more easy to use, a calibration toolbox that will enable the user to align multiple Aria glasses and GoPro cameras and other DSLR you want to bring into the same frame of reference. So you can do this multi-camera setup recording yourself, right? We're going to release a web-based MPS user portal, so you can just upload all your data, go to lunch, check on your phone the progress of every single processing, and come back when it's ready. We will also exploring to see whether we can release more machine perception service capability, like the hand stuff that Jacob's talked about. We haven't come to a very concrete list of what we're going to release, but just look for it. We will have more things to come. Definitely subscribe to the newsletter that Ed is going to send out to all the folks. All right, with that, I'm going to hand over to Vijay, who's going to give you a hands-on demonstration of how easy to use some of the open source tools.
Hello, everyone. My name is Vijay. I'm a software engineer on Project Aria. And today I'll be demonstrating how easy it is to use the Project Aria open toolset. Okay, at a high level, we'll be running code in Python in a Jupyter notebook. We will see how easy it is to open an Aria VRS file and examine the data in it. Then we will switch gears and try to load some of the MPS output that Jacob talked about. And then in the end, we'll try to use the Aria's calibration APIs to put everything together. All right, time to switch the computers. Thank you. Awesome. So here's the first notebook. The goal here is to see how easy it is to load a VRS file and examine the data inside it. I'm going to restart it. Cool. So the first cell is boring, whole bunch of imports. I've already ran pip install Project Aria tools inside this virtual environment. Matplotlib, and we'll be using the Aria pilot dataset, one of the sequences from Aria pilot dataset today for the demonstration. Okay, that went through. Now, this cell shows how to reopen a VRS file and examine data in it. So we create a data provider. That's your go-to place for reading anything from a VRS file. Once you create the provider, we get all the streams in the VRS file. And then what we're doing here is if it's a camera stream, then we print the stream ID, camera name, and the frame rate. Otherwise, we just print the stream IDs. And towards the end, we read the RGB frame, a random RGB frame, and then use good old Matplotlib to show the image. So let's see what we got here. The stream IDs, stream names, and the frame rate. Eye tracking camera, RGB, and so on. And here's one of the images from the stream. Just a few lines of code to get going. Okay, this is good, but let's make it more fun. First time I ever anytime I record a VRS file, I want to see what's in it, not just one image, but like everything in it. So for the remainder of the demonstration today, we'll be using this tool called Rerun that is great at visualizing data, and then we'll be sending data to it through the Aria's Project Aria tools APIs. Okay, so here we create an RR instance, the Rerun instance, and then we set some options on the data provider. Essentially, we are truncating the first 48 seconds and the last 288 seconds and just stream the middle, because that's where the interesting content is. And we again start the streaming from the VRS file. We get the timestamp, and then we just draw it. We basically, if it's a camera image, if it's an image data, then we draw it, and if it's a sensor data, we plot it. So let's see what happens. Okay, there. Okay, this is in device time, and here what we are seeing here is SLAM camera feed, RGB camera feed, IMU, eye tracking camera, everything in one place. Just with a few lines of code. Notice how the images are tilted. Remember that. We'll see how to fix that. Okay, with me so far? All right, let's switch gears now. We've been talking a lot about machine perception services. So so I took this sequence and then uploaded it to our MPS service. It got processed and I downloaded the data. Now we'll see how easy it is to consume the data generated from the machine perception services. Here, our goal is to use Project Aria tools and to specifically look at the MPS APIs. Most of it is one line. You just give it the file path and say load it, and everything just loads. All right, first part. This is again a whole bunch of paths, constants, and helper functions created just for the demo today. I'll skip the details, not really important, but we'll just restart everything. Okay. Let's run this. All right. Okay. In this first cell, what we will do is we will load the MPS point cloud, the point cloud that Jacob showed, that's one of the sequences. And then the point cloud that you get from MPS, machine perception services, includes all the points. So here we will be filtering out some of the noisy points so that we can look at a cleaner point cloud. So again, just one liner, you load it, it loaded 2.9 million points. And then here's a filtering function that filters points, that rejects points based on some parameters. Okay. So now here we'll actually draw it. And then in the background, we'll also load the point cloud observations. There we go. Okay. Does this look familiar? This is the same kitchen that you've been seeing today, right? That's the stove, there's some appliances, kitchen cabinets, countertop, etc. Super easy to load. Okay, let's go back. Now, I said that as part of the semi-dense point cloud, we also expose all the observations. Like Jacob said, it includes which point was observed when, where in 3D and on 2D, basically the SLAM image, and at what point, like at what point in time. So let's see. So here, what we will do is I'll run this and show you later. So here what's going on is, again, I'm creating the same data provider that we saw in the previous notebook. I'm telling it to only stream SLAM cameras because I want to draw the SLAM cameras and overlay the 2D observations on it. Again, I handpick a duration that looks cool. And here's the code. Essentially, we start streaming. We say, hey, if it's the left camera, draw the left image, get all the 2D points that are visible here, and then block them. And the same thing for the right camera. All right, let's see it finished rendering here. So let's play it from the beginning. Oops, too fast. Okay, here you see the global point cloud here being projected onto 2D images, 2D SLAM images. Again, just a few lines of code, super easy to use. Okay, so that was global point clouds. Now, before we proceed further, I want to give a quick primer on the coordinate systems that we have. We have the world coordinate frame that everything is attached to. The MPS point cloud that we provide is in the global frame of reference. The MPS trajectory, which is the 6 staff poses, those are again attached to the world, but they tell you the pose of the device at any point in time. And inside the device, we have device is an arbitrary frame of reference, which is what the poses are generated in. And then we have all these sensors, the SLAM camera, RGB cameras, and the central pupil frame, which is where the eye gaze is coming from. And then the eye gaze that is generated from MPS is attached to the central pupil frame. Now, I don't know about you, but any time I am using a new system, as soon as I get the trajectory, for example, here, I want to draw it. First thing you draw is always an XYZ coordinate frame color coded, red, green, blue, right? And you see if it's looking decent or not. So let's try to do that. It's running. And oops, that's not what I wanted to do. All right, here. Oh, that's too fast. Let's play it again. So this is basically raw MPS poses visualized in 3D with the point cloud. I will minimize the camera images here, not very interesting anymore, but that looks like somebody moving in the kitchen and cooking, doing stuff. Right? Again, one line to load the poses, and then for rendering, you can use whatever package you want to use. There's plenty of them available. All right. Moving on here, this was just one line to load, and then I pre-selected a start index and end index based on something interesting to show. And okay, now you've been hearing about Aria's calibration. We're very proud of it. I want to just show you that we really mean it. It's really good. I call it watertight. It's so accurate that there's really sub-pixel accurate. Take a look at this image. This shows all the sensors and their coordinate frames roughly on the Aria device. Notice the SLAM camera here. The left SLAM camera is here. The right SLAM camera, this is the RGB camera, and then the right SLAM camera is here. I've been working with some of the university partners, and often they have trouble getting all these sensors in the same frame of reference. I want to show you how easy it is using the Project Aria tools calibration APIs to consume this and make sense of it. So what we're going to do here is, again, use the same trajectory that we loaded. We'll replay it, but this time, instead of just one RGB coordinate axis, we'll see 3 frustums for these 3 cameras. And let's see if they're accurate. I just ran it. Okay, let's zoom in here. Let's turn this off. Can everyone see it okay? Okay. I'll go somewhere here. Okay. There. All right, let me zoom in. So what's going on here? I've basically applied extrinsic calibration from Aria on top of the trajectory. So let me turn them on one by one. You remember the left SLAM camera and RGB camera are close to each other. So that's the left SLAM camera. That's the RGB camera right next to it, right? And that's the right SLAM camera. And now if I play it, it's all going to move together because it's rigidly attached. This is what we expect. So far it's telling me that my system is working fine. The code I wrote has no bugs. All right. Good so far? Okay, that's a sample of extrinsic calibration. So here, essentially, I use the APIs to the calibration API to get the extrinsic calibration of RGB camera, SLAM left and SLAM right. And I just applied that in the scene graph. Now, just like MPS trajectory, all the extrinsic calibration is also always with respect to the device frame, which is arbitrary. To get to any sensor, you can use the calibration APIs to get its exact pose. Cool. Now that was extrinsic calibration. Let's look at how easy it is to use the intrinsic calibration. You remember the cameras were rotated and also distorted. So here, what we'll do is we'll try to undistort an RGB image and display it again in the scene. You see how it's coming together slowly, right? All the pieces. Again, I will run this and then we'll talk about the code, what's going on. Here, I query the device calibration API to give me the RGB cameras calibration. This is the intrinsic calibration. And I want to undistort it into a pinhole model. So here I just create a pinhole model based on certain width, height, and focal length. I deactivated all the other streams and only activated RGB stream. And as the data is being streamed, as the images are coming in, I am undistorting it. I'm basically getting the raw image, rectifying it. This is basically undistortion using the pinhole model that we just defined above. And then we'll draw the original image, and then we'll also draw the rectified image in the frustum to see how it looks. All right. Let's zoom out. Okay. I will deactivate the SLAM and RGB cameras here. And this is essentially a similar frustum that you saw in some of the other videos. And if I play it, okay, it's starting to play. And then here on the left, you see the RGB feed. Okay, I'm going to pause there. And you see how this is distorted, right? Okay, where is our RGB undistorted image? Okay, it's in there. So it's now rotated correctly thanks to the extrinsic calibration. And look, the distortion here is already corrected here. This line is straight. And I'm going to play over it a little bit. There. So now what you're seeing here is the camera feed, the poses, the point cloud, and everything coming together. My mouse skills are not very good, especially on a trackpad, but you get the idea. You're right. Cool. Again, this was very simple, just a few lines of code to load data, correlate everything in space and time, and put it together. Okay, the last piece that I want to share today is the MPS iGaze. Again, by now you're probably used to it. Just one line to load the iGaze. This was again generated using machine perception services. And because let me scroll up here a little bit. The iGaze is always expressed with respect to the central pupil frame, which is in between. It's an imaginary frame of reference in between the two eyes. So again, I load the extrinsic calibration between the CPF frame and the device frame. And then we stream the eye tracking camera stream. And then for each timestamp, we grab the nearest eye gaze. We convert the eye gaze is expressed as yaw and pitch angles today. So we convert into a 3D vector and then we draw it. All right, let's go back. Let me turn off this image for a minute and show you. Okay, there. So you see this small offset between where the pyramid starts and the eye gaze origin. It's the CPF offset from the RGB camera. And if I turn on the RGB camera feed, okay, that person is gonna come back, then it will make sense. Yeah. So you see how eye gaze precedes the user action. See, the person is already looking before they turn. It's very, very easy to visualize all of this. Now I want to pause here and see what we have here. For this to work well, a lot of things have to come together. The global point cloud for context, the trajectory for telling where the user is, the intrinsic and extrinsic calibration. Like this video in the frustum will not look perspectively correct if any of the things go wrong. The calibration, the poses, MPS, I guess everything has to work correctly. And this is all easily accessible. Essentially, everything I am running here is all open source code that we exposed today. And you also saw how quick and short it was in terms of number of lines. That's it for the demonstration. So thank you again for coming. And I think we have a break now for 20-25 minutes, and then we'll resume again.
They're going to get that working. They're trying to get that working. Yes, absolutely. Yes, absolutely. And I think actually, and actually use that as a So the youth, their team London. And they are more seconds and got the entire scene from there. Improved over time. We're doing a demo tomorrow in August on that, and we're there are obvious parallels when that goes to and we have a loader about really exciting. All of these are ready to go together. They one of them extremely high and using So there's no like expectation. The research people Thank you very much. Yeah, I'm going to go stop at go up to Whistler for a couple of days. Yeah. Thank you. Okay. Oh yeah.
It's fine. Yeah, it's fine. Yeah.
Well, okay, so asking for it, so then I'm making my laptop on my table, so no, but if you can show show me something.
do I have to do? No, we're not doing that. Great. So then so you don't need doctor. Alongside. It's also weird.
It's a picture. I'll just put this slide. Yeah. Just put this side. Huh? Sketches? वो घूम रहे हैं अच्छा उसको स्टैप करेंगे
sequences that were captured simultaneously. And we had things like speech to text so that we could open up opportunities to explore challenges in contextual AI. And the data set was separated across two different types of domains. The first was across everyday activities, which were captured by actors, essentially role-playing some of the scenarios that we expect people to see throughout their everyday environment. And of course, where there were sequences that were captured in the same frame of reference, those sequences were then aligned to the same space-time reference frame. The second set of domains for the Aria pilot dataset was this desktop activities. Essentially, this was a Aria wearer surrounded by multi-view cameras so that we could explore challenges with object detection and tracking tasks. And one of the interesting outcomes from this first release of the dataset was the segment anything model by the Meta AI team actually used this dataset and used the eye gaze as an input to their model. So that was last year. This year, we're very excited to announce two new data sets. Those are the Aria Digital Twin and the Aria Synthetic Environments dataset. I'll take these through just a high level, one after the other. The Aria Digital Twin dataset is, we believe, the most comprehensive egocentric dataset with a high quality corresponding ground truth. What do I mean by that? Well, in this video here, you'll see in the top row, we see the real world footage as it's come directly out of the Aria device. In the row below, we see the simulated ground truth. Essentially, this is a synthetic copy of the real world that we can use for interesting research challenges. In order to build this, we had to accurately digitize the entire space, as we can see a fly through here, which involved LiDAR scanning the environments and then doing manual tweaking to make sure that the synthetic digital twin is as accurately aligned to the physical world as possible. We'll hear more a little bit about how this was captured later on from Carl. What this allows you to do is then to take those annotations and propagate them back into the real world footage. So you really truly do have this comprehensive ground truth of the real world. That's Aria Digital Twin. The second dataset that we're announcing today is Aria Synthetic Environments. And this is the first procedurally generated synthetic Aria data for large-scale ML training. What do we mean by large scale? Well, what you're seeing here is just a snippet of one of the 100,000 synthetic scenes that we use for scene reconstruction tasks. Taking a look at some of these trajectories, we essentially have 100,000 unique scenes where we're simulating Aria trajectories throughout those environments to make sure that within those sequences, the observers are looking at every single part of those scenes. And of course, because this is entirely synthetic, we have comprehensive ground truth that we can also use, whether that's the RGB image, the depth map, or instance maps for those same environments. And uniquely with the Aria Synthetic Environments dataset, we also have this CAD-like language that is able to describe the scene using something that's equivalent to architectural commands. So we have something like make wall, make window, make door, describing exactly how that room is laid out. Now, for these two challenges, or pardon me, for these two data sets, we have two challenges. So for the Aria Digital Twin, we actually have two different challenges. We have the 3D object detection and tracking task, the scene generalization, and then a second challenge on top of that is few shots 3D object detection and tracking. The difference here being that for the second task, we don't include the objects that you're trying to track within the training data. For the second dataset, the Aria Synthetic Environments dataset, we have a scene reconstruction challenge that requires you from seeing a sequence and then translating to that architectural language that we described before. So these are the datasets and challenges. Please do have a look online at projectaria.com and have a look at those datasets. But this isn't, of course, just about us from Meta building these datasets. This is already also about enabling the community to use Aria, capture datasets, and make those available to the wider community. So in order to do that, we have this second pillar of the open science initiatives, which are open tools. We really believe in accelerating the state of MP and AI research and believe that we can do that together with the community. I'm not going to repeat some of the material that we've seen earlier on today with the open source tools that can be used to dig into these data sets, but it's not just about the Aria data sets alone. We're also releasing tools that are valuable outside the Aria ecosystem, such as VRS, the file format that we use to write out time series data, whether that's from Aria or our Meta Quest line of devices. So do please have a look at that on GitHub. So those are tools, data sets. Finally, open models. And when considering which of the models that we use internally we actually open source, it took us back to why we produced the Aria program initially. This is really about how we can demonstrate responsible innovation, and responsible innovation starts with privacy. Prince mentioned that the pipeline that we use for data collection that is outside in public spaces goes through an anonymization pipeline to obfuscate faces and license plates. What we're doing in the coming months is that we are open sourcing this model so that if you are capturing data, whether that is with Aria or any other type of device, we can anonymize that, obfuscate faces and license plates to ensure that the researchers are actually focusing on the work that we need to be doing rather than having to reinvent the wheel. So those are the open science initiatives as part of the Aria program. We've got data sets, we've got tools and models, and this really is just the beginning. So we're really excited to bring everybody along for this journey with us. Please do have a look on our website and sign up for a newsletter at projectaria.com/newsletter. And from that, we'll make more announcements about tools, challenges, models, and data sets in the coming months. With that, let me please hand over to Carl Wren, who's going to take us through a little bit more detail about the Aria digital twin dataset and challenges. Carl.
Hello, everyone. It's me again. I'm just presenting this on behalf of our team because the folks who are working really hard on this was also the one who worked really hard on open source tool to push the release for CVPR, so they didn't have time to do the presentation. I'm just helping the team to do the presentation. Okay, so the table of content, 4 things that we need to answer. What is the Aria digital twin dataset? Why did we build it? How did we build it? And what is next? It's the same fly-through video that Ed has already shown. So it's literally by the name, Aria Digital Twin is captured through a Aria sensor suite with Aria sensor simulation. It's a digital twin. That means you have a physical existence of that space, but you also have a digital replica, one-to-one replica of that space, right? So just looking at the number, what we provide in this data set, there are 2 spaces. One is the very quote-unquote famous surreal apartment that you have probably seen many times in previous data sets. There is a data set called Replica a couple of years ago, which has this space captured in there. There are also fair papers on embodied AI that use this space for some of their experiments as well. We also have a pretty empty office space. There are a few hundred sequences, and there are hundreds of objects, including stationary static objects, as well as dynamic objects. You have single person activity who manipulate things, do their daily activities in those spaces, as well as multi-person interaction. So you have a third person observing, a third person view to observe someone doing certain tasks in those spaces. All right, let's now come to the more important question. So looking at the number, right, it's 2 spaces, a few hundred sequences, a few hundred objects, not very impressive. Why did we build this in the first place? Right, if you look at the overall landscape of all the 3D perception, scene understanding, object recognition type of data set, there are plenty. We're not the first one to try to build a digital twin data set. And there are Objectron, tons of objects, 3D oriented bounding boxes, and there are all the scene related data sets, and there are workshops running in CVPR that talks about those challenges and data set. But what is the missing piece? Right, then we need to really zoom out to look at what the data sets in 3D machine perception is used for. It's used for training and evaluation. When it comes to training, of course, the quality, the quantity of the data set does matter. And there are a lot of techniques around how do you get away with lower quality, lower resolution, lower accuracy, less complete data set at a very large scale. But for evaluation, what we really think hard about is the quality matters. If you don't measure your algorithm or your system very carefully to the level of the application requirement, right, you can't really make a meaningful improvement. So this data set really focused on the evaluation side. So here's the claim. So Aria Digital Twin is the most complete and high quality data set for egocentric machine perception tasks. What does that mean? So comprehensive and complete can mean many things, but specifically under this context, complete means in these two spaces that we have complete ground truths of everything, including the environment, the objects, the state of everything, and human even as well. Comprehensive also means we derive all type of ground truths that is meaningful for this egocentric machine perception tasks. All right. So first of all, let's do some kind of a virtual visual Turing test. So one of those is modeled and rendered through our simulation engine. The other is a real capture from the camera. Which one is real? Which one is synthetic? Quick guess. Yes, you can tell the left is real probably because of the sensor noise that is more realistic, right? But imagine if I just hide the left image, which I didn't have a slide on that. If I hide the left image and you only look at the right image, would you think that's a real photo captured from actual lens, right? Okay, next one. This is from a SLAM camera, the monochrome camera. Okay, which one is real and which one is synthetic? Yeah, probably from the sensor noise as well, right? So it seems that we didn't do a very good job to add enough sensor noise to fool you. But again, you can see the left. If you only look at the left image, you will think probably that is a real capture, right? Okay, now let's do an even harder one. So this object model, this is in our data set. It's the famous birdhouse that we worked on a lot. Which one is the real capture from a camera, and which one is the synthetic version? So the right one is real, or yeah, left is real. I think that the little thing is here, right? There are more noise on the flowers, and it's too perfect on the right. So to talk about the quality, so these are the. Let's just zoom in and look at all the ground truths that we're providing through this data set. So this is on the leftmost column. So this is all the raw sensor streams. So we're only showing the cameras, but we also have IMU simulators as well. And we have the simulation with all the state of objects and scene rendered, right? And we have 3D oriented bounding boxes, 2D oriented bounding boxes, 2D axis aligned bounding boxes, 2D segmentation and depth map. But just look at the 3D bounding boxes and 2D bounding boxes. They're not just like loosely placed bounding boxes. They're super tight because we have the 3D models, right? These are the minimum bounding box that actually includes the object, both for 3D, 2D as well. And segmentation mask is also, doesn't come from an image segmentation like edge-based, for example, a segment and everything, right? This is from the 3D model itself. And the depth map, you see there is no artifact. There is no strange artifact from the structured light sensor or time of flight. Everything is pixel perfect. So because we have this type of very accurate simulation, digital twin, we can even provide this level of ground truth. When you have the table actually occluding the chair, you get that level of segmentation. And same thing, when we're working with the fisheye lens towards the edge, there is this vignette, right? We can exactly give you where the signal is not good enough and give you a cutoff on that. So this is the quality of the attention, the level of attention to detail in this data set. And you might ask, well, how can I trust that your model alignment for everything is perfect? We do, again, it seems that we talked about that we care about calibration. Yes, we do. Our team cares about calibration a lot. This is the end-to-end arrow calibration. So you see that's a very thin stick, and you have OptiTrack markers on it, right? To be able to measure how accurate we are in the end-to-end system, which includes many arrow compounded, right? You have the headset tracking arrow, you have the object tracking arrow from the OptiTrack, you have the time misalignment between the OptiTrack system as well as the Aria timing system, and they all compound into a single arrow in the end, which is the reprojection arrow. So what we do this is we manually annotate the center of every single dots, okay? And then we have the OptiTrack system track individual dots. We project those dots onto the manual annotation, okay? On top of that, we also solve for a 6-dot pose out of the manual annotation, and then reproject solve the point position in 3D into those cameras. So you have basically 3 estimated 2D point location. And if your calibration is really good, they should overlap with each other on the same spot, right? This is what we basically achieved in this level of accuracy. You can see most of the dots are, overlapping with each other with a few pixel offset that we just cannot handle with such a big complex system. And how accurate we are. So we have a big table of all the objects' accuracy measured in the way that I just described, right? Pixel reprojection error on average on the camera, we have around 6. So this is the measured reprojection error in pixel versus the optimized reprojection error. The optimized reprojection error is after you annotate the point and then you reproject the point to there, is about less than 1 pixel error, right? So for every object, we have this metric. But we also have more than objects. So for people who are collecting data, doing operation in the space, they're wearing a OptiTrack suit, as well as their hand has a wrist band that measures where their wrists are. So this is what you get when the, Yes. So this is similar to the machine perception services example that you just saw from Jacob's presentation, as well as from Vijay's presentation. The only difference is the complete state of the environment is also exposed as ground truth, such that you can conduct contextualized AI research that Richard hinted at from the beginning, because this is kind of a bypass everything, and you already have the ground truth for everything. You keep all the state up to date. This could also enable certain near-term use cases, for example, like human segmentation inside of this segmentation mask provided from ground truth, as well as if you want to just use 2D contextualized information is what people are looking at, such that you're segmenting that region or inferring the user intent just by the 2D projection of the gaze. All right, why did we build it? So I think the explanation of the data set itself is already giving a lot of motivation behind why we built it. So this will enhance a lot of existing research, which includes 3D object detection and tracking, scene reconstruction, and view synthesis, like nerve-related stuff. Is to just lift the benchmarking that you can do with those type of research to the next level. It will also empower a lot of research that was not possible or not possible in a very accurate way in the past. For example, simulation and real image domain gap analysis. A lot of research are pushing you to use simulation for training, but you actually don't know how much really the difference between your simulation domain and your real domain. This gives you exactly that tool to do some analysis. Same thing with contextualized AI. It's a complete state, maintain the spaces, and you can conduct this type of research on top of that. How do we build it? On a high level, it's a very expensive and engineering-oriented process, very tedious, and then we have to make sure everything goes right. So the whole tracking system is relying on 2 components. One is the OptiTrack system. The other is the Aria glasses self-tracking and the localization. As Jacob described, we have a very good SLAM system that tracks itself with very low drift, right? So we need to merge the 2 space frame of reference into the same one with very accurate calibration. The body tracking is achieved through this bodysuit, and all the object models and spaces are captured through an industrial-grade LiDAR and laser scanner. And all the materials and light conditions are calibrated manually by tech artists. So this is effectively recreating a 3D movie using like Hollywood-grade quality production. Right, it's a very heavy lifting process, and everything has to go really together. We feel it's important for us to bring this to the community, because think about it. I mean, no university is going to create this type of space and just to conduct conduct some research, right? But if we do this and provide this to the community, a lot of university and research institute would be able to do this. All right, what is next? I think this is really a bad joke, because Prince just used this, but in here, with greater data set, it comes with greater challenges, right? So with this data set, we're hosting 2 challenges, as Ed just introduced. So 3D object detection and tracking with scene generalization. So for this set of challenges, all the objects you have already seen it in the ADT dataset, but it's in a completely new environment that you have not seen it. The second set is a few shots 3D object detection and tracking challenges. So none of the objects are within the ADT dataset. You will see it in for the first time in a new dataset, right? But we'll give you a few frames, a few seconds of data that captures the poses and appearance of those objects, and you should be able to, well, we want you to be able to track them. It's $10,000 for the first place, and the challenge data set is open now. So these are the set of data set that only have the raw data, doesn't have any annotation, right? You run it through your own algorithm, you submit the result to our website at a later point, and you will get your measured result. The deadline will be in November, and we'll invite participants to talk to our BMEC workshop. So just give folks a sneak peek of the space, what it is. So we have more than 2 digital twin spaces. There's a supermarket that we fully modeled. But people might say this looks like probably a supermarket, any supermarket in 2020 when COVID is still around, right? It's pretty empty, but we will put more stuff in it. But it is the new environment that we will put into the challenge that is not in the ADT data set. And please go ahead and check out the data set and download and use it and participate in our challenge. All right, now I'm going to hand over to Chris to talk about the synthetic environment data set.
Cool, thanks a lot, Carl. Let's see. I got it right on the first try. Cool. So my name is Chris. I'm a research scientist at Reality Labs Research, and I'll be presenting this data set called Aria Synthetic Environments, short. It's ACE for short. So what is ACE? This is a large-scale synthetic data set consisting of 100,000 unique procedurally generated interior scenes. So to our knowledge, this is the largest indoor data set to date, or that's currently available. So we're setting a new precedent for scale for these data sets. And this little video here basically shows you some of the diversity of the scenes that we've generated. Furthermore, we're also providing a full set of annotations with each of these scenes to facilitate egocentric machine perception research. So why create another one of these indoor data sets? I did mention there's already a few out there. Well, these data sets typically fall short for a few different reasons. For example, we have this data set, Structured 3D. It provides professionally designed 3D layouts, which is very nice, high quality. It comes with stuff like semantic labels and a bunch of goodies, but there's only 3,500 scenes, right? It's a bit small. Then we have Proctor from AI2, and they have 10,000 scenes, but these scenes, which very similar to ours, are procedurally generated. This is meant for embodied AI. So they don't provide egocentric trajectories, renderings of each scene, etc. So can't quite use that one either. Then we've got SunCG. This one's a bit older, but it's a bit larger too. It's got 45,000 scenes. But the annotations in this data set are lacking. There is only depth maps and volumetric ground truth, which doesn't exactly enable all the research that we would like to facilitate. And it's not available at the moment due to some legal issues. So can't use that one either. Then we've got the Zillow indoor data set. And this data set, unlike the rest of them, is a real data set, real world, collected by basically collecting panoramic images, a sparse set of panoramic images at each house and stitching together that floor plan. But this one is very small. It's 2,500 scenes. Again, it does not provide egocentric trajectories, so it doesn't allow for a full evaluation for egocentric machine perception. So these data sets, they kind of lack in one dimension or another, but most of them in general are just a bit small. And as we've seen in recent research like ChatGPT, GPT-4, or your favorite LLM, large data sets are really enabling remarkable gains in machine learning. So here's just a table that compares ACE at the top row there to the data sets I mentioned before and a bunch of other data sets. And so not only is ACE the largest indoor data set currently available, it also provides egocentric trajectories. It provides photorealistic image renderings. It provides depth maps for each of those images, segmentation maps, and it also provides ground truth layout. So only a few of the data sets focus on ground truth layout, which is a fundamental problem when it comes to scene understanding. So with all these annotations, researchers like you guys can use it to study problems like pose estimation or regression, layout reconstruction, scene understanding, all from an egocentric perspective. Additionally, because ARIA synthetic datasets is an ARIA dataset, it includes some of the outputs of our pretty cool machine perception services that you've heard about in the before. So for example, each scene comes with a semi-dense point cloud representation. So I'd like to highlight one kind of cool advantage with this dataset, which is that there's a real world component to it. You've heard about our ARIA program, our ARIA partner program from Prince. And because of that, or thanks to that, our academic partners can get access to ARIA devices and the machine perception services for free, I think. So that means any model you train on this data set can then be deployed on an on-device super awesome demo. And we're really excited to see what you guys end up doing with this data set. We're highly encouraging researchers who have ARIA already or are signing up to get ARIA to please check out the data set and train some models, do some cool stuff. Okay, so let's take a look at the data set. What does it contain? So as I mentioned, there are 100,000 unique multi-room scenes. As you can see, there's a small snippet here. Each of these scenes are populated with 3D objects from the Amazon Berkeley dataset, which was released in last year's CVPR. So we've got some household objects in there if you look really, really closely. For each of these scenes, we simulate an agent walking around the entire scene, and then we render sensor data from Project Aria rig at a 10 hertz frame rate. So here I'm just showing the RGB stream of the simulated agent walking around the house. We also simulate IMUs, SLAM cameras, etc. Because we have this simulated ARIA recording, we can then plug it through our machine perception services pipeline and get stuff like semi-dense point cloud representations. Cool. We also, as I mentioned, provide ground truth annotations. It's a simulated data set, so we have the ground truth 6 stock poses of the trajectory, so that can facilitate pose estimation, pose regression research. We've got 2D instance segmentations on the right there to facilitate segmentation research. We've got 2D depth maps, so you can study problems like video depth estimation or even monocular depth estimation. And then we also have the floor plan in what I'm saying is a CAD-like language, and Ed has already alluded to what this is. So let's take a moment and dive into that a little bit. So in this slide, I'd like to highlight this representation. Our dataset ACE is providing the ground truth layout in this textual representation that has these procedural commands like make wall, make door, and make window. It's kind of like a CAD-like thing, right? And this format contains all the parameters necessary to recover the geometric entities that you see here on the left, the walls, the doors, the windows. So most architectural layout estimation methods, they typically directly predict the geometric representations. For example, they'll predict the corners, the edges, and try and connect them into a wireframe or something like that. But this formatting suggests that there are alternative methods to produce floor plan layouts. And this is exactly one of our intended goals. By releasing the ground truth in this format, we're encouraging researchers like you guys to investigate prediction of the scene geometry in this text-based format. And the challenge that Ed mentioned will also further encourage this. I'll talk a bit more about that in a bit. All right, so some statistics that's always fun to look at for the data set. There are 100,000 scenes, as I've said probably for the 3rd or 4th time. And in each of these scenes, I mentioned that we are simulating an agent walking around. So some fun facts about these trajectories. There are 58 million images in this entire data set. There are the agents, the simulated agents are walking around for approximately 67 days. It's a long time to walk. And the total distance walked by these trajectories or these simulated agents is about 7,800 kilometers, which is roughly the distance between London to San Francisco. Yeah, that's fun. Each scene has up to 5 complex shaped rooms, all of which have a Manhattan world assumption, which means that the walls connect at a 90-degree angle. And as mentioned, this is a very large data set. It's approximately 23 terabytes when it's compressed. So hopefully you have a, well, that's actually pretty small for a beefy hard drive, right? Just a quick overview of how this data set was generated. There's 3 phases. The first is we procedurally generate floor plans. So here, what I'm showing is essentially the floor plans plotted in, and you can see the rooms, they're connected, etc. Then we take those, extrude them into 3D, and we populate them with objects from the Amazon Berkeley dataset that I had mentioned. Here's a top-down render of a single room of one of these scenes. So you can see you got some beds and couches, lamps hanging from the ceiling, pictures on the wall, etc. So they're all a bunch of household objects. Once we have these scenes, we simulate those trajectories. And so on this image here, we see the blue line there shows the trajectory of the agent walking around. And then from that simulated Aria recording, we can pass it through the machine perception services to get semi-dense point clouds. And you've seen a bunch of them already this talk, but here's yet another interesting visualization of those semi-dense points reprojected back into this particular image. Cool. Just a slightly deeper dive. That first phase, floor plan generation, is a procedural generation. We designed heuristics that basically say add one room after another, and we have some constraints like they need to be connected, they can't be overlapping, etc. We also randomly place doors and windows, which you can see on the external walls with these cyan, or I guess from here it looks a bit teal, and orange little lines there. Then if you extrude that thing into 3D, and then you cut out holes for the doors and the windows, you get a little mesh that looks something like this. So with that thing, we want to fill that with these objects. Again, from the Amazon Berkeley dataset. There are about 8,000 meshes there, all household objects, which is very fantastic because we are simulating houses. And we populate these objects in a semantically plausible fashion. So we again designed heuristics that basically say stuff like the bed should be placed against the wall because you will rarely ever see a bedroom where the bed is in the middle of the room. Chairs and tables, for example, are not placed against the wall. They're kind of in the middle of the room. So here we just have a few top-down renders of some of those houses. And the last and final piece, here we're seeing basically another visualization of those agents walking around. And these trajectories are simulated with more heuristics again, that basically say we need to visit each room sufficiently. We then simulate the Aria sensor data, including images like you see in the middle here at a 10 hertz frame rate. And then we can plug that into machine perception. And here's yet another visualization of those semi-dense points, this time from a top-down render. And the more yellow pieces are where there's more cluster of points looking from a bird's eye view. We will be releasing a white paper in the following weeks, which will have a lot more information about how the data was generated and data set statistics and whatnot. So please stay tuned for that. Cool. So I've just covered, what exactly ACE is, what it's got. We're also providing some software tools to get researchers up and running really, really quickly with this data. So one of the first things we provided is a very, very simple download script. Once you sign the agreement and you get access to the data, you just have to run the single command to download either a couple of scenes or the entire data set. Up to you. We've got some really nice loading and visualization tools. We've seen some from VJ. That's really nice. This one is a slightly different set, but all of them run in Jupyter notebooks and are very, very lightweight. So you can get up and running very, very fast. We've got code to read dataset files like the point clouds, the trajectories, etc. We've got interpreters to reconstruct those geometric elements, the walls, the doors, the windows from that CAD-like language. And we also have visualizers in 3D. We also have projection tools using Aria camera intrinsics to either reproject points into the scene or even cast rays into the scene. So all of this it runs on Jupyter notebooks. So once you download some of the data, you should be able to get up and running very, very fast. As I mentioned here, it's very simple. You can easily get started. We also have a visualization in Plotly where you can look at all modalities in one go. Again, all of this runs in Jupyter Notebook, so should be very low friction, and hopefully you can just use the code, plug into your data loaders, and get those models training like tomorrow. Yeah, and the projection tools. Here are some semi-dense point clouds back projected into those simulated ARIA images. And as I mentioned, you can also use those tools to cast rays into the scene in case you're interested in doing NeRF-style volumetric rendering research. So there will be a white paper coming out very, very soon in the coming weeks that will detail all of this information, much more details for that. So please stay tuned for updates at projectaria.com/newsletter. Last but not least, Ed alluded to this, that we're hosting a scene reconstruction challenge with this data set. So the task is, given an ARIA sequence, like we were seeing here, output a language description of the scene. So this is the layout, and in particular, we're looking at walls, doors, and windows that you can kind of see here, back projected onto the image. But the key point here is the language description. So this is what I showed a few slides ago, that text-based representation. The goal of this challenge is really to encourage researchers like you guys to tackle estimation of layout using these text-based representations. We think this is a really cool avenue of research going forward. We hope you're very interested in participating in this challenge. We're very excited to see what kinds of things you can do to make this work. And of course, to really get you interested in this challenge, there's some prize money, $10,000 USD. The results will be announced at BMVC later this year, just like the ADT challenges. The challenge will go live very, very soon, in a couple of weeks. So again, please stay tuned for updates. You can find ACE on the projectaria.com website. So please check it out. Cool, thanks a lot. And I think I'm handing it off to Raul.
Hey guys. All right. So I'm a PhD student at Carnegie Mellon, and I work on all right. So I'll be talking about one of the projects I did last summer with the Aria team. It's called as Ego Humans. It's fundamentally a data set project, but let me motivate this first. So there have been many 3D human data sets so far. 3DPW from Munich, Panoptic Studio from CMU, very popular, Human 3.6M, 3DHP. However, they are mostly captured in indoor settings. 3DPW is the only outdoors 3D data sets, but it contains at most 2 humans in a sequence. Apart from this, the activities showcased in the data set are slow, like standing, talking, walking, etc. Also, on a minor note, from the aesthetic perspective, it's about time we replace them. You can see the video resolutions are pretty low. So yeah, to address all of these issues, we constructed the Ego Humans dataset. This took around 8 months to complete. I just wrapped it up recently. These are some visuals from the dataset. As you can see, we are no longer constrained to indoor settings, unlike previous works. And we made it a point to focus on dynamic activities like fast-paced sports, like playing volleyball, fencing, frisbee, soccer, badminton, tennis, playing tag, some interesting indoor sequences as well. Most importantly, our activities are completely unchoreographed. There is no step-by-step script given to subjects on how fast or slow they should move. And the actors are they're just performing a specific task or playing a game. And this allows us to capture the natural motion of the actors. So what enables us to go in the wild? Our capture setup is very simple. It consists of many tripods and GoPros and the Aria glasses on these subjects as the ego view. And this allows us, Aria Glass's state-of-the-art camera calibration allows us to take a 3D metric system and then establish in any location. And that allows us to generate like high quality 3D ground truth. So this is just an overview of a typical capture setup. Ego glasses, as I said, GoPros running at 4K, 60 FPS, capturing the static person view. And these are the annotations we provide. So pretty much everything bounding box plus tracking ID, 2D poses, 3D poses, and then also meshes. And to get to the point of generating all these annotations, these are sort of the sub problems you have to solve. This is the visual schema. So first, I'll talk about data capture. This is the multi-view visualization of one of our sequences, volleyball sequence. I'm showing around 9 cameras out of the 15 cameras. Everything is time synchronized and the cameras ensure complete 360 coverage of the activity. And this is another example of people playing Frisbee. This is the Aria view. All the left stereo, right stereo cameras along with the RGB camera. And all the actors in a scene are wearing Aria. So the ego views are also time synchronized. This is like a 4-person 2v2 volleyball match. You're seeing 4 Aria views simultaneously here. So once you have done the data capture and then solve for time synchronization, to obtain good 3D annotations, you need to get good camera calibration. And this is the hardest and the most challenging step. So first, let's talk about the moving cameras. You can see this is the 6 DOF camera poses for the entire sequence on the right in yellow, and the 3D scene points in the left. The ego glasses are calibrated, as you know, using VIO. And unless you do some really fast motion or maybe tripped your leg, generating huge motion blur, I think VIO-based calibration works pretty great. Once you do this, you need to align all the Aria glasses and the 3rd-person static cameras in a single consistent global coordinate system. To that, for this, we use structure promotion, giant structure promotion optimization, get all the cameras in a single coordinate system. And because Aria glasses have IMU sensors, then we can do this in like a metric coordinate system. So unlike previous work, we can anchor our global coordinate system to a metric unit. This allows us to generalize across 3D setups. Next up, so once you've done camera calibration, you need to solve for detection and tracking. We saw that like off-shelf tracking methods do not consistently perform well in like crazy conditions. So as all the humans in our sequence wear the Aria glasses, we already know their identities and the 3D location, right? This gives us a good region proposal for bounding box detection and tracking for free. This is like a good illustration here. As you can see, even in extreme or complete occlusion, look for the left image here. We can still detect and track humans, the red bounding box in the left. All right, so once you have done for tracking, this next step is getting poses per view. This is straightforward. We use like an off-shelf state-of-the-art model trained on Coco dataset to do per view 2D pose estimation. And then finally get all these 2D poses per view in 3D using triangulation. So conceptually, this is pretty straightforward, triangulate with Ransack, but there are tons of heuristics here and post-processing steps because you can have noisy predictions per view. So yeah, detect outliers, error correct, all of that. So this is one of the visualization of one of my favorite sequences. We have Jacob and Chris fencing it out. And I'm showing the final 3D pose reprojected to the camera view. As you can see, our poses are robust to dynamic human motion. And because it is multi-view, robust to any kind of occlusion. So you can get this kind of see-through effect. This is the multi-view visualization of the same sequence. Yeah, you will observe that even in case of complete occlusion, we can still extract accurate key points. So those were static cameras with moving humans. Here are moving cameras capturing moving humans. Again, 3D pose reprojected to all the ego views. We can see all the 3 ARIA views here along with the stereo perspective. Next up, so this is the final step, obtaining meshes from 3D key points. We use the SMPL body model. It's a nice parametric body model to represent 3D meshes, low dimensional, and we fit it to the 3D poses. Yeah, 3-stage optimization, just first optimize for the root and translation, and then fit for the body shape, and then optimize for the pose, and just keep doing it iteratively. All right, so this is the mesh visualization of a 4-people sequence, outdoors playing tag. You can see people are running, abruptly changing motion direction, and we can capture really subtle movements in arms and legs without using any markers, and outdoors. And that was like a completely virtual view of the 3D scenes. Let's see how good does the 3D match with the pixels in the image. So I'm showing the overlay here. Here's the fitted SMPL mesh reprojected back to the camera views. On the left is the 3rd-person view. On the right is the 1st-person view. As you can see, even with fast camera motion, our mesh estimates are pretty good. And yeah, this is the multi-view visualization of the same sequence, all the 9 cameras again. And the same drill from the Aria views. Cool. This is the volleyball sequence. So yeah, you will see players doing all sorts of crazy things, jumping, diving. And the Aria view, all the 4 players together. And the tag sequence. And the Aria view for the same tag sequence. All right, yeah, so that was some of the sequences we have. Once you have collected all this data, you can now train a model to reason from the ego perspective. So I'll not go into the details of this here, but we basically train a 3D tracker, which can just do tracking just from the Aria view. So given left, right, and RGB image, it can output human meshes, but across time, so with human identities as well. And here is a comparison of our model with baseline tracking methods. So for the ego view, due to huge camera motion, you will often see that 2D methods, they suffer from a lot of ID switches, but our method is able to fix those ID switches because of it being fundamentally 3D. And yeah, next up, this is like a sneak peek into the next follow-up project we are doing. So this is the prediction of off-shelf method we have on crazy scenarios, like where there is extreme human-human contact, for example, hugging here. As you can see, everything fails. Current methods are not designed to handle human-human contact. And this is another example which we are doing, where there's like a grappling sequence, 2 people are wrestling. So the setup is similar. We have static cameras, but both of the players are wearing Aria. So yeah, this is ongoing right now. We hope to make some progress here. But what you are seeing right now is the current state of our results here for this sequence. You can see there are no obvious misses, as you saw with the off-shelf methods, but there is still interpenetration error or yeah, collision. So we are working on improving this right now. Hope to show it very soon. Cool. Yeah, that's about it. Please check out our project page or the code and data. Thanks.
All right, time for Q&A. So I will ask all the presenters to come up over here. And we can have questions from the audience. There is a mic in the center of the room. So if people just want to come up to the mic to ask questions, and then we'll answer questions from here. So all the presenters come up front. Carl, Vijay. Okay. Yeah. So we'll come over here to answer the questions. So whoever has questions, please come to the center and ask questions in this center microphone. We can monitor the Zoom. Yeah. Don't feel shy. Ask questions about anything. Project Aria, about Aria Research Kit, any of the new data sets and challenges.
And also, what is missing from Aria? So what is the sensor data that you want that we're not providing? What are the services that you're interested in seeing, be flawlessly generated automatically from the data? We assume you want something more than what we've currently provided. So this is that opportunity.
Well, this is Lynn. I have a very new question. Since Meta has a product that's already, pretty widespread Quest, is there any data set reuse from the Quest collected data to Aria? Just like a really new question.
So is the question, is there any data sets that combine Aria with Quest?
Yeah, because Quest has the forward-facing cameras too, which
Yep.
can collect, for example, my own apartment, like
Right.
if I want to do something.
Oh, okay. So, I mean, Prince, you can answer this, but you mean because you've already got a Quest,
Yeah,
instead of getting an Aria device,
yeah,
can you?
something like that.
Okay, because you can get an Aria device, right? Projectaria.com. Sign up. But yeah, Prince.
Yeah. So you think of it this way, right? Quest is a VR device. You can run VR applications on that device. And Project Aria is a research tool which allows you to capture data and run all these machine perception services. Technology is new research, new applications that you build using data sets from Aria device. You can actually deploy them on a Quest device as well. Remember the BMW example that I showed, where the data set in a moving vehicle was collected using Project Aria devices, but the applications that we showed in the example were actually running on the Quest Pro device in the car. So use both these devices. Both devices serve a different purpose. Use the Project Aria device to collect data sets, then do new research using those data sets, but then you can use the Quest devices to deploy your applications.
Oh yeah, that answers perfectly. Thank you.
Thank you.
So I have mind to apply your data set to view synthesis task. But to do that, I think there are something missing, because considering that your data set may play a role of ground truth, probably writing information or surface material information in terms of BRDF will be quite required for that kind of task. Do you have any plan to extend your data set in that direction?
I think this is for the ADT data set, right? In the current release, we haven't released the 3D model, the material files and all of that, not because we don't want to, because we are going through kind of a legal process in whether we can even release some of the models that we captured ourselves. For example, certain of the cereal boxes and product has design patents behind it, right? They have their own IP that we are not be able to release them. There is a process that we're currently going. Of course, we want to release the full scene, the mesh file as well as the texture file, the material information to the community, so you can do the maximum amount to really do the research. But at the moment, we're going through that process. If we can clear that, we'll definitely release those. Yeah.
Hi, just a quick question. I want to know, what's the restriction of using the data, and is there any license and limited to just research, or is open to commercial use of using the data for training model and use it for commercial purpose? Yeah.
So currently, when you go to the website and you apply, you'll see the full license terms as well. It is currently restricted to research use for the data sets. But if you have specific applications in mind, I think on our website, there should also be contact information. So if we update the license terms and expand it later for commercial terms, then we will, one, notify through the newsletter. And then if you have certain applications in mind, you could reach us through the email address as well. But currently it is restricted to research use. But we have opportunity to expand it later as well.
I see. For to expand the license, what's is there any annual fee or like what's the process?
No, for getting access to data sets completely free. Just apply. Even getting access to Aria Research Kit, like the research kit that we provide, both the classes and all these services are actually free. For getting access to the classes, because we have limited number of classes, you do have to apply, submit a proposal. We'll review the proposal, and then only select few actually get the classes. But data sets is available to everybody. All the tools are available on GitHub to just download. Data sets are available on the website to download as well.
Okay, yeah, sounds good. Yeah, thank you.
So I come from the manufacturing domain. So my question is, do you foresee possible application in manufacturing, as an example, in monitoring and supporting manual operation like assembly, disassembly, or other, let's say, not so consumer-based application? Thank you.
Yeah. Honestly, the world is your Aria oyster. So if you think that is a useful thing, for example, getting where people are, interacting, where they're looking, space-time information about where they are, this is absolutely for you to apply and to try it. We really don't see the restrictions to exactly the kind of mixed reality applications. And I think at the beginning of the session, we sort of really talked about this future where there's a lot of applications that really are around the state of reality and not necessarily about 3D display technologies and so on that might be associated with these glasses and augmented reality and mixed reality, virtual reality. But instead, Aria takes us a step in the direction that says there's actually no display there yet. But certainly you can already get information that's very valuable to give feedback in a training session, for example, or in general over distributions of people trying to do things. And with our partners in Ego 4D, we're starting to see the potential of getting data sets that help basically say that there's value in an analysis of the data, even if that's after the fact. So you might collect a data set with a distribution of people for a week, then analyze it, and then look at that data and learn something from it that's very different from, say, a single user consuming and interacting with their environment with the glasses with the display modality in mind. So yeah, please apply if you're interested in that.
All right, great work overall. We've seen a lot of great data sets today. I guess my question is, I think several data sets we introduced earlier, I think ADT, ASE, they are all static scenes without any other dynamic agents. Is that right?
No, I think ASE is dynamic. Sorry, ADT is dynamic. Yeah. So
Okay.
ADT includes I'm not sure if it includes the humans. Carl, do you want to speak to it?
It includes one or two agent for human actors and around 37 dynamic object that people are moving around. Oh.
70 dynamic objects.
Yes, 70 dynamic objects, and then the rest of the scene are static.
Okay. So yeah, sorry. Maybe the question is less relevant. Maybe in the simulation case also, are there ways to add kind of interesting agent behaviors so we can do research beyond perception, but also robotics, where we need to kind of marginalize the future risks?
Yeah, well, I'll get Xiaqing, who is the tech lead on this project, to address that.
Tech lead's first question is, what's your question again? Sorry. My question, I guess, on the simulation data set, whether we can do kind of robotics side of research where you kind of predict what other agents are going to do, and so you can kind of marginalize over what you want to do as well. So for example, you want to collide, you don't want to collide into other agents in the scene. I'm not sure what's the things you need on your side, but the thing the ADT will provide is the ground truth of the human. And we do have like multiple users in the scene as well. So you have the ground truth for both of them. The same thing applies for the synthetic thing. Is like you have the ground truth for them and they are perfectly aligned. So. All right. In the synthetic one, the ASE, we don't have other agents, right? That's for Chris.
Yeah, there are no dynamic agents in the scenes. We don't currently have plans to go in that direction, but it's definitely something we can consider. Yeah.
Cool. I think just to connect the dots, there is a FAIR habitat project that puts agents into simulated environment, and they use our historical data set, which is called a replica, which is kind of a less high quality data set than these two. But I think if you draw the connection between these two, right? You put agents into simulation, now we have better simulating environment. Definitely there is a way to do that type of research.
Hi, thanks for the interesting talks. I'm really curious from an applications perspective. I mean, this vision about AR and VR, bringing in more human-centered and like more personal vision of computing in the future. Kind of connecting back, probably this is not the intention when you said this, but connecting back to this question of like sensor data. I mean, this is quite a broad question, but have you thought also about kind of like sensor data related to like the person wearing the device? So I guess that like one thing that you talked a lot about as well is like how vision and audio and all the rest of this is very high bandwidth. Maybe some of this personal data is much lower bandwidth. Maybe it's just a simple trivial thing to add those kinds of sensors, but I was kind of curious about your vision on that side of things. Thanks.
Yeah, I mean, just to put something specific on it, when you say personal data, you perhaps are talking about biometric, like health indicators, heart rate, PPI, oxygen. Yeah, I mean, I think what's interesting is there's a lot of that information in these data sets that are undiscovered. So when you have a high quality, for example, accelerometers that are on the head, on a device that by definition is touching basically the bone of the nose, or at the very least connected to 3 points, then actually that accelerometer data has a lot of information in it that, potentially both on the side of we need to understand the privacy concerns of that data, but actually the signals are there for things like heart rate through the head. Now, they're not going to be super high quality, and we haven't optimized them for that. But from a research perspective, like I say, both sides are important to understand. We go to great lengths to anonymize bystanders in the ARIA data, and it may be necessary to actually do the same even for accelerometer data. So we need that data for trajectory estimation, but we shouldn't necessarily be measuring heart rate if that's not what you want. Now, of course, this is a research tool, not a product. So the data is there to have a look at. For the future, I think pairing glasses with other devices and building new data sets that are combined is very, very powerful. And again, that is something that is just a sea of things for you to try and build new data sets with your Aria devices. There's nothing stopping. You don't need collaboration with us. You just need a device, and then go and collect your data sets, combining, some Apple health indicators together with Aria, and release that under some sort of like, permissive license. I think that's a very exciting area. I'm inspired by the work that Raul did with basically the Ego Humans work. And you can imagine pairing things like heart rate together with some of that for performance sport analysis, and you start to get an incredible tool for sports science. And the same is true for various other areas of health, I think. But yeah, it's the tip of the iceberg, and go forth and collect new egocentric data sets, safely, yes. So yeah, that's a good question. Like, what are the other sensors that you're looking for? Would a heart rate monitor on a head be good? What other information do you think is important? I mean, I'm interested, has anybody here actually used eye tracking before? And if so, what have you used it for? and what kind of data in that eye tracking made or was good or bad. What was the point at which the data was high quality enough versus really you might have been using eye tracking, but perhaps it wasn't high enough quality. We're interested in understanding that as well with all of you. So what's the precision of the sensing data that's needed? What are the new modalities? So any other modalities? Or the area is perfect, and that's okay. It's perfect. It's good.
If you can go to the mic. So hand is very useful. Hand tracking and detection is very useful, for projects. We have been using it on HoloLens too.
Yeah.
It's very fundamental for things such as procedural task learning. So we really look forward to using it. I have two questions, now that I'm on the microphone. Can we use the MPS in an online fashion? Do the detection, tracking, or we have to basically start the session, end the session, upload it, and then basically get the results of the MPS. Can we do it online? As the data comes, maybe we run it and get the outputs of the system. And more importantly, I want to ask about whether you guys are actually working on really bringing AR into Aria, because you started by saying you have great form factor, you get lots of modalities that like HoloLens and others get, but they have AR, you still don't have the AR, and we really want to use it in many applications for actually like AR and guide users. Is there any active project bringing AR into the system?
I think so. Actually, I mean, it's I can get on my soapbox for this because this is why we're doing Project Aria. We think it's a red herring, and anyway, go and use HoloLens. It's brilliant, especially HoloLens version 2, right? So then it's like, why aren't people walking around with HoloLens on? And what are the applications that are not enabled when you put a display on your face so that you need a HoloLens form factor or a Quest Pro form factor? The same, it's got pass through. And that's this difference of sort of like the potential research. You can't wear a HoloLens or a Quest Pro all day. You certainly can't take it outside safely or ride a bike or, and all of those things that we've just seen, ego humans, you cannot do that in those form factors. So does that mean it will never be possible? The answer is no, but we know that the gap between building something that has a display in it, like a Quest Pro, and in a form factor that looks like an Aria are sort of 2 points that are quite far apart in terms of sort of like reality. So not just from a price point of view of building the device, but literally physically making that plausible. So I think one day, and that's of course the holy grail of AR, is something that's like Aria, perhaps even lighter, not 76 grams, but 30 grams, lasts all day rather than a few hours, has displays in it, that's the holy grail. But I think the point at which we will see that will have seen several value propositions of things like Aria, at least in research, showing that you don't need to have immediate mode interactions through a display. You can, for example, pair AirPods with Aria through a companion app and utilize it in streaming mode, which I think we talked about. Good. And actually prototype it. So streaming mode already allows you to run your algorithms as you might want to with whatever code you have available. But you did ask the first question, which is MPS available in real time or runtime? I don't think we're talking about that.
So right now it's not available in real-time mode, and it's not possible to run all the payload on the glass as a current stand, right? We don't have that much compute power. At the same time, it's the processor's doing a lot of other things. However, if you remember my part of the talk, we did show a demo ourselves that's running things off a NVIDIA Orin puck through streaming and through the SDK, right? So that would mean that any researcher from today, if you take an off-the-shelf state-of-the-art SLAM system like Orb SLAM 3, right? You take another detection module, well, probably eye tracking is too preparative because it's dependent on the camera and the whole setup. You can already run things similar to it, maybe not to the full extent. Whether we can expose and provide, maybe software libraries that has pre-built capability in there, I think our PM team is working through kind of a conversation to how can we expose that, and is this more value to the community to have access that and whatnot. So we definitely have the capability internally. We're finding the right engineering solution to be able to provide that to the developer and user.
And I think I'd love to know, we'd all love to know and share these experiences, because we use HoloLens too for research, you know, for various different things as well. You know, it's available for everyone to use in that way. But why wouldn't you use HoloLens V2, right? So what is it that HoloLens V2 doesn't do that actually you would want like something like Aria with a display to do? And if the answer is, oh, we want the HoloLens V2 features, but in an Aria form factor, we all want that, right? And so then the question is, how do you make that happen? And the answer is there's a big gap in display technologies to shrink it, in power, performance trade-offs, in the weight trade-offs that mean that at some point you just add more weight and then you can't wear the device without having quite a big mount and so on, more like a HoloLens or a Quest Pro. So it's a brilliant problem. If there was a solution there, I think we'd see those devices already. Certainly I don't think Aria is positioning itself to try and do what Magic Leap 1 or a HoloLens 2 does. Is actually quite a unique proposition of something that's much closer to glasses, so you can get these data sets that are really much more ecologically real. You know, walk into a space with your friends and actually play a game and really feel fine doing that. But you do have to trade off that you're not going to get real-time feedback in this generation. But yeah, it's on the wish list. I think there was another question.
Hi. So I think you mentioned that there's like 6 microphones in the device.
7.
7. Okay. That suggests that there's something ambitious there, because if you just want to capture sound of the environment, you would need just one.
Yeah.
But the whole discussion was about more vision applications, which makes sense since we're at CVPR. I just wanted to know a little bit more, what are the ambitions there, and what do you expect people to do with the 7 microphones?
Brilliant. Yes, very good. The spatial microphone array, kind of like eye tracking, is I don't know if we can put this microphone up a bit. It's fine. Just lean forward. Okay. Get real-time direction. Yeah, unique. So as we saw, it's really obvious, this data like eye tracking, where you look before you touch. It's what humans do. We've evolved that way for a good reason, right? We want to get the signal. On the spatial time of arrival, this is incredible signal of sound and where it's coming from in space. For example, speaker identification from a point of view of who's speaking, not their personal ID, but who is speaking. And that's the kind of signal that we use a lot of course, like as a human, you know, someone speaking from this side or that side. And that's, again, combined with vision technologies, produces a whole area of research, which is really quite new. So I think that realistically, I think we can point you to some papers that we have released already with the audio research teams at Reality Labs using the spatial microphone array. But it's things like that. Time of arrival is indicated through these microphones. Speaker, the wearer versus environment. Another very significant difference. If you only have one microphone, it's very hard to disambiguate me speaking versus someone speaking close to me. Whereas you start to be able to develop algorithms that can say I'm speaking versus the other person is speaking. And it's great for various reasons, as you can imagine. Yeah, any others for audio? Oh yeah, another one, which is simulating. So the data sets that we showed are also very good for simulating sound propagation. So we've got essentially that paired Aria with a digital twin, and you can start to use those in very interesting ways for applications where if you do have a digital twin, you can simulate audio, simulate the propagation because you've got the head pose with very high accuracy and orientation. You can simulate the arrival sound that should be being played into the different basically speakers. And so you need those combined head pose with high accuracy and also the environment and some other things that give you the transfer function for the human's head and ears. But that's right. So that's the application spaces for spatialized audio as well. Any more sensors? These like requests. We're interested. Anything that's on there that we don't already have? No, not even from Chris. No new sensors, Chris. We're doing good. Yeah, go for it.
All right, so the Aria glasses, they're fixed on a person's head. And it seems like the main sensing paradigm is we somehow believe that the head is the most important part of the body to sense. If you think about maybe like the future of like computing, we're probably gonna have all kinds of sensors in our house, on our clothes, shoes, clothing, like smartwatch. There seems to be like a whole ecosystem that's probably going to develop over time.
Yeah.
So I was wondering, should we be working on that instead, or should we be working on that as well? That it's not just glasses, but it's like a whole ecosystem. And then if we have that, what does that look like now? What do the algorithms look like? What does the communication look like? And what can we do with that?
Love it. So this morning we called that distributed machine perception, and we put it as like number 3 of the most important sort of like problems to be solving. I think the useful thing is that glasses, you can put glasses on a tripod, right? You can put glasses on a desk, you can put glasses on a shelf in a research lab, and you can use it as a proxy for a spatialized visual, audio, or multimodal, basically distributed sensing system. So I think the answer is yes. Now, the fact that when you get into the domain of how much infrastructure would you need to put into environments versus the potential that humans carrying the infrastructure with them very elegantly solve where should the infrastructure be problem. And they take it with them, and so it's tidy afterwards, and you don't need to install, and humans will keep updating those devices if they add value, whereas you've got to completely re-infrastructure those spaces every single time. I think it says that actually the answer is yes, but really we should really be nailing the glasses one first, because that is such an elegant solution to the infrastructure problem. And the alternatives, and certainly from our own research internally, trying to infrastructure spaces with cameras for visual modalities is really very, very hard, if not impossible, because of occlusion, resolution, and various other placement problems, bandwidth of data that would be needed to capture from this environment at the level that a human actually could obtain from their Aria devices today is basically impossible. And yeah, you can see what a capture lab looks like with OptiTrack and so on, right? It's really, that's what they look like. It's plastered absolutely everywhere. And as we're seeing out of the work from your lab, maybe we can start to get towards algorithms that can estimate that all from just egocentric data. So I think the answer is yes. And I'm sporting here my Aria badge. That may be another device in the future. You have to come to the next tutorial to find out what this actually is. But yeah, it's a great question, Chris. So you've got any intuitions as well, or do you like the elegant egocentric solution as the holy grail?
I think as like a vision researcher, that's where I started. So that's kind of where my passion is. But taking a step back, thinking it doesn't have to be glasses.
Yeah,
there are many other modalities, and I feel like we're kind of, in some sense, kind of blind to that because the community, or at least the community that I'm in, there are many other ways to like sense things much easier. And you're talking about infrastructure. I mean, if it becomes common enough, like electricity, it's just things that are it's gonna exist already in the infrastructure, and those standards might change over time. We certainly have like Wi-Fi now, which we didn't have, 30 years ago.
Yeah.
So it's probably a little bit of both.
I think so. So we online we've got a project that really is this superstructure research project for our team that Aria has been built to kind of enable and start to get things out in the wild, and that's called Live Maps. And this is effectively this thing which is like there's many sorts of sensors, maybe cars, maybe robots, maybe infrastructured cameras from like home security systems that you want to plug in, and enable that data to have a sort of a synchronized space-time frame of reference so that it can be fused into essentially a map that then acts as sort of like, the available resource for all devices. So that's the superstructure. And then you need to start somewhere with a set of devices and solve those hard problems of space-time frames of reference, and hence the SLAM systems get done first, and you move up that chain sort of thing. So I think we're getting there. And indeed, there's no reason why the practical solutions to like very high resolution, very high quality infrastructured spaces are not actually, they're probably very likely, frankly. There's reasons why we do have certain cameras in our homes for security or in offices and so on. And that Live Maps is the missing bit that actually would unlock distributed machine perception. And working on that in earnest in kind of like an open way, a framework, a web for machine perception, if you like, I think is really a thing that a lot of folks have been thinking about for a while. And it still is yet to happen. With Aria, we're hoping to sort of say, look, here's some devices, they already provide a space-time frame of reference. Maybe we can start to look at live maps again in a new light.
All right, thank you.
Yeah, thanks, Chris.
Excellent questions. I love it. It was very interactive. Any other questions? If not, maybe I'll just ask Richard for one final closing remark.
Wow. All right. This is always a good opportunity. You know, I said it right at the start, which is like what this opportunity is. Let me see if I can find the slides. Whilst I do that, I want to thank, of course, all of that Aria team that put this together, and everybody for attending. You know, whether you were in a session now, watching it later, when we've got the videos, etc. It's been great, and this is the second year. So I think it was Prince who sort of said, you know, this is the year where we've kind of built a lot of the foundational technology, and we are now in a year of scaling. And that means partners. That means building the relationships with exactly the PhD students, you know, master's students, postdocs who want to run labs full of Aria devices and get these novel data sets with new modalities, right? And we're trying to make it as low friction as possible to be able to get the data sets, start to utilize the kind of services that we expect to be really quite standard, like SLAM, and not have to solve those problems again and again before getting started on actually the real research as we see it, which comes after things like SLAM. Not to slight anyone working on SLAM here. If you are doing a PhD, it's still a very hot area. Okay. But yeah, it really is the opportunity to work together. So I think, let me find this and just read it one more time. You know, I think the real breakthroughs, whilst they may sometimes seem like they're always in a slightly adjacent field, like this year it's generative AI with large language models, right? Trained on internet scale data sets. Well, I think if you join a few dots together and say, like, how far can that research go versus that's prime time now for basically big product groups in big companies and small product groups in small companies to productize that technology. But there is a gap between what that technology can do and what we want AI to be able to do. And that gap is context. And if you cannot get that context, it seems very unlikely that AI can be that useful for you in most of your life, most of the time. So the real breakthroughs are going to come from solving essentially how you can get that context. And that's going to be built on something like distributed machine perception from wearable devices. And frankly speaking, if you look in CVPR this year, there's an uptick in teams working on egocentric because data sets are starting to be released, but it absolutely is at the beginning. So if you're interested in being in a field that, whilst it's got its precursors in robotics and HCI, and a lot of us like Chris and our labs have been doing this now for, you know, decades, really it's always been sort of adjacent to where the spotlight is. This year's spotlight, generative AI, it can only go on for so long, whereas this is the beginning of really like a space where a lot of people's investments in technologies for 3D computer vision, for human computer interaction, for adjacent fields like robotics actually come to light. And realistically, the value proposition is at least as big as sort of the LLM based AI that's been built on textual data sets from the web, but now in a space of reality. So bringing basically a lot of that power, but to essentially your physical environments, your physical lives. And bringing people back into reality is, of course, the main aim of what we call the second great wave of human-oriented computing. And we all want to do it together. So thank you for attending. And we look forward for all of your submissions for Aria. And thank you, Aria team. Thank you. All right. Thanks. Are we doing that party? Hi. Yes. By the way. Yeah.
Yeah, I didn't, I guess.